c'è l'audio perché i microfoni sono spenti. Certo che è spento. Non so se... Emanuele, is it time to start the meeting? Luca, you have to stick 5 minutes to go, no? It is still 5 minutes to go. No, we're starting at 9. Ora si dovrebbe sentire l'audio, non si sente. Hello, this works. Does this work? Yeah. Shall I start? Do I have your permission to start? Buongiorno and welcome to the 12th edition of the Arcetri workshop on plasma astrophysics. We have a pretty good crowd here. Hi, Gang. I didn't even say hello, everybody. We're only 10 minutes late, which is early in Italy, as you know. And especially here. I think we did a pretty good job finally of distributing power. I think there's even some pretty far up there. So anyway, welcome. When we have some late cancellations, the third talk, Marco Valli, will not be here. Are we going to just... He's sick. Yeah. He will not attend at all. And we don't know about Jefferson, whose plane was canceled, and I don't know if there's other cancellations. So we have to swap the schedule around a little bit. But we'll see. Let us know if you want us to change things based on those modifications. Probably we should get started. We usually, the talks are a little shorter this year because we have so many of them. But, you know, when you're popular, what can you do? You have more people. We'll have a chair. Who's chairing? You chairing the first one?
No, I did not share.
Where's Emanuele? Where's Emanuele? Okay, come on, you could be a chair. See, the reason for having young guys on the organizing committee is to get them to be chairs. And as usual, we sort of encourage, permit open discussion. So I'm going to turn it over to Emanuele Papini.
I don't know who's not coming today, but Marco is not here, so done.
Okay. Okay, so you can introduce the speaker.
Okay, so we will start with the first session, which, as many of you know, is about solar wind in the inner heliosphere, and particularly this session should be devoted to talking about PSP and solar orbiter results. So we'll start with Chris Owen, that will talk about solar orbiter SWA observations of electron strahl properties inside 1AU. So you have, the talk is scheduled to be 20 minutes, 15 minutes plus 5 of questions, but as always, we are a bit elastic, a bit.
Do I need to do something to...
What do you want to do? First
I guess people in the room want us...
Yeah, first problem. Yeah, it should be work.
It's on the TV?
No, the projector is off, of course. That's why, yes, that's why.
Emanuele, the big pointer is over there.
The projector was off, I'm sorry. The projector was off, that's why.
Okay.
There you go. Do you want to use this one or?
I can use this one.
Good.
Is that right enough? Oh, okay, good morning everybody.
I will sing at you when you have like 3 minutes.
Okay, I'll see how fast I can. So this is my first attendance at one of these meetings, and so being given the first talk is maybe a bit of a hospital pass, as you used to say when I played rugby. So I hope I've hit the kind of hit the style that you're used to. I am going to talk a little bit of science that I've been doing with our solar orbiter electron instrument, but I am aware maybe that that maybe not everybody in the room has been following the story of solar orbiter, so I would just like to show, the reason I'm doing this is that I have the honor of being the PI for the solar wind analyzer instruments on solar orbiter, and you see the graphic of solar orbiter there. The sun is facing away behind the heat shield, but our instrument is made up of 3 sensors. One of them that measures the proton alpha. Sorry, where is it? The proton alpha particles. It's just tucked in this corner. A heavy ion sensor, which I guess Ben will talk about a little bit more in the next talk. Is that right? Yep. And this talk concerns mostly the solar wind electron analyzer system. So I've just put the picture of the FM there. It sits on the end of the boom, a 4-meter boom in the shadow of the spacecraft, and in principle can see the whole sky apart from where the spacecraft is blocking. And just to sort of talk about the status, I'd like to advertise that maybe many of you in this room will be interested in using our data or comparing your theoretical results or simulation results to our data. Many of you may know that we had a bit of a rocky ride for the cruise phase, the 18 months of cruise phase. But I would just like to say that as of now, our sensors are all working pretty well when they work. We've had some issues with operations and some performance issues that we're still working on. And in particular, the last week has been a bit tricky. There was a major turn-off of the whole spacecraft Thursday a week ago, and it's been a bit of an adventure trying to get our instruments turned back on. But I guess the message for this group is that we have, since the start of the nominal phase about a year ago, we've been building up quite a nice data set. And what you see here is just a table of the data that you can currently get if you go to the public archive. You can use the data from there. And if you want to see what days have data and which ones don't, then I can give you this link later on. And just to advertise, so this is data that we got from the PASS team from OM, and basically this is data that was downloaded over the weekend. This is the latest data we have on the ground. It's from early September. Some of you may know that early September is causing a bit of an interest. There was some CMEs go through, so you can see here that this is the PASS energy time spectrogram. The velocity in blue, the temperature in red, the density down here. So you can see there's a lot of activity here. You can clearly see the difference between the protons and the alphas. There's some cold plasma. So I think that there is likely to be quite a lot of activity, probably combined with Parker Solar Probe as well, on these events coming up in the next few months. So just to sort of then move on to, I think, the science that I want to report, which is to do with the measurements from the electron instrument. So as I said, we have some performance issues, particularly at low energies, where we'd put the instrument on the end of the boom, trying to get it away from the spacecraft so that we would have no ill effects from spacecraft charging and photoelectrons. It turns out that that isn't entirely successful, so we still have quite a lot of work to do to clean up the data at lower energies. But once you get above a few tens of EV, so in this case I'm talking about sort of 50 EV and above, we have a very nice data set of electrons in what you would call the Strahl energy range. So this is just an example shown here. So the top panel here shows the magnetic field, actually in spacecraft reference coordinates. And what we do is take the data from those two heads that I showed you in the instrument picture, rebin them according to the magnetic field direction, and we come up with a pitch angle distribution. So this is 6 hours of data, just showing the phase space density of the electrons as a function of their pitch angle with respect to the magnetic field. And so you can clearly see in this case there is a strong beam going on and off here in the anti-field direction. So that's the kind of thing that we're looking at, and as I say, I think that is good for Solar Orbiter. That helps with one of the major goals, which is to establish connectivity. I think that's an important part of the connectivity. But what I'm going to report here now is just some of the things that I've been doing to try to characterize some of this data. So why have I done this? So as I say, we have these good measurements that are clean and good to go in the upper energy range. So what can we learn? So just a couple of things here that people have talked about over the years. For example, Matt Owens was maybe a decade ago, did quite a lot of work talking about the balance between the focusing of the beam as it moves out into lower field strengths against the processes that act to scatter it. And there's quite a lot of material out there that discuss how that works with distance and different spacecraft, different energy ranges, etc. Milan, I guess, has a history of talking about how the Strahl population may be scattered to form the halo, so we can look at that kind of thing as well. And perhaps a little bit more recently, there's been some interest in asking not only whether there is a beam towards the sun, but a deficit in the part of the distribution that's along the magnetic field. So some of the Parker Solar Probe data has been used to look at that. And it's maybe a signature of the exospheric models of solar wind. So that's what I'm trying to do. What I've done is a very simple analysis, I think. So I've taken the electron data and the magnetic field data pretty much for the first sort of quarter of this year nearly, which is when the spacecraft was moving from close to the Earth in towards the sun. We now have the data for the second quarter of this year, so I could certainly, if I had time, update this analysis, but what I'm reporting now is basically the run in towards the sun for the first nominal phase perihelion. And all I've done is basically reduced our 3D data into sort of a 1D pitch angle slice for the energy range above about 50 eV, and what you get is a plot something like this. So the symbols here are the data themselves, and as I explain in the next slide, I just do a simple fitting to this to work out what the pitch angle distribution looks like in this higher energy range. So my simple fitting result looks like this. All I've done here is to take a constant background. I consider that maybe that there is a Gaussian that is peaked near the 0 degrees with a certain width, and maybe a Gaussian peaked at 180 degrees with a certain width, and the factor in front here, I allow it's open so it can be positive or negative, and I'll show you some examples of that on the next slide. And then I try to categorize the results by looking at how much the part of the distribution near 0 degrees pitch angle exceeds that near 90 degrees, and how the part near 180 degrees exceeds that near 90 degrees as well. And so I calculate these parameters, and if there's a factor of 2 difference, I say there's a strahl beam. If it's less than minus 0.5, I'll call that a deficit, and anything else is just a kind of a quasi-isotropic distribution. So just to show examples of what I'm talking about, this first one here is the one I showed earlier. So clearly there's a very strong beam along the field direction near 0 degree pitch angle. So this scores highly on my beta, so this is a strong parallel strahl beam. In this case, I get a strong beta at 0 and at 180 degrees. So something like this scores as a bidirectional strahl beam. But then I come to this other category that it's possible that my coefficients are negative. So in this case, there's a deficit here in the distribution. So that scores less than minus 0.5. So this is, in my categorization, is a clear anti-parallel deficit. And then anything else that may look something like this, I mean, by eye, you might say, well, there is some kind of beam there. But this doesn't reach the thresholds of factors of 2, so this just gets put into the quasi-isotropic bin.
Are they one day of data each? How much data in each plot?
I'll show you. So each plot here is one sample. There's about 1/3 of a million samples that I've analysed this way. So these are just examples of, these are 1 second data taken every 10 seconds or every 100 seconds.
So 1 second of data produces one plot like that?
Yes. Okay, and so then the numbers, okay, there's a lot of numbers, I'll try and take you through them. So the total number that I had between January the 1st and March the, whatever I said it was, oh, it's here, March the 12th was over 300,000 points. And, okay, I haven't discussed the fitting criteria. I do have a kind of a score that says this is a good fit, this isn't. I can talk to anybody that's interested about that, but about 225,000 score well. So that's those two. So it's about 72% of the samples I seem to fit acceptably to this very simple criteria that I used. And then if I look at the split of these things between the 0 degree pitch angle, the 180 degree pitch angle, and the quasi-isotropic, it comes out sort of fairly evenly balanced at sort of 30 to 35% in each of those bins. And the interesting thing that I think that then comes out, or that says that something is working right here, if you like, is that if I then split those between the measurements that were taken when the radial component of the magnetic field was outward and the radial component of the magnetic field being inwards, then I get a clear split. Okay, so most of these strahl beams, so 73,000 there, 59,000 there, compared to 9 and 10,000, are moving away from the sun. So that's exactly what you expect. There's only a small number that come back. And in fact, the number that have bidirectional is only 6,000. So a fairly small category there. The interesting thing then maybe is the same thing kind of happens with the deficit. So there's about 10,000 samples that show this deficit in each direction. And again, though, it's kind of the other way around, that the deficit appears in the sunward going part of the distribution, which is, again, I think what's expected from the predictions from some of the models. And I should say that this part, the 3,000 deficits moving away from the sun, is maybe overestimated because that's the bin that is blocked by the spacecraft. So there may be deficits that are created by the fact that the magnetic field comes through the spacecraft and you can't see it. Am I allowed to stop for questions? Yeah.
Sure. Yeah. It exists when also the strahl is pointing the opposite way. So
You mean, do I see?
so when deficit is anti-sunward is when the strahl
That's a good question. I haven't explicitly looked to check.
Because those would be simply like switch mix, right?
That's a good question. I haven't looked, so I can't answer that right now. So, yeah. So then I've just got a few slides, I think, now where I just try to sort of show you that data en masse. So I just then tried to take all these data points and plot them to show you how they appear in as a function of other parts of parameter space. So there's a bunch of plots that look like this. So here, the red plus symbols are all of the strahl beams, and the blue dots are all of the deficits. And here, in this case, I plotted the width that I get. So from my Gaussian, I get the width of the strahl. So I've got the width, and in this case, I'm plotting against the magnetic field strength. And so you can sort of see where things go. And I've just tried to do a very simple linear straight fit line through these to show you that kind of like, okay, for the width of the strahl looks like it increases with magnetic field strength. The width of the deficit definitely increases with the magnetic field strength. And in each case, those lines, however, are too slow. The width should be changing faster than that if it was just adiabatic focusing that was driving this. So that, I think, confirms the ideas that there's quite a lot of pitch angle scattering that goes on to keep this beam wide. Just down here, the second plot here just shows the percentage of the good fits that fit in every range. So obviously outside there's not many events, so maybe take a pinch of salt for this one, but and clearly the deficit is strongest here because there's a dearth. I think that when I get round to looking at the rest of March and the outbound leg, I'll fill in a lot of this magnetic field strength regime because we go through perihelion, so naturally the field strength should be stronger. So I was hoping to have updated these plots for the meeting, but it didn't happen. So I can just tell you that I'm pretty sure that I'll get more data in that region. Okay, so now this is, so I also then looked at the speed of the solar wind at the time of each of these measurements. So this is the same format, except now we've got the solar wind speed along the bottom, otherwise exactly the same. So what you can see now, I think if I just drew my best fit straight line, that the strahl tends to be narrower in faster wind. Again, I think that's something that was kind of at least anecdotally known. The deficits, however, seem to stay sort of pretty much the same width in pitch angle as a function of the speed, and tend to see slightly more strahl as a proportion of the good fits at higher speeds and slightly less deficits. I'm not entirely sure what that's telling me, but that's the result at least. And then finally, I think just looking at how this varies with radial distance. So again, it's a bit patchy because of as I said at the beginning, we've had some sort of on and off times for the spacecraft. So because I'm just talking about data taken on one run from 1 AU into 0.4 AU when the spacecraft or the instrument was off, there are gaps in this. And that would certainly again be filled in when I do the analysis for the outbound leg. And in fact, for this leg, once I get the perihelion data in this as well, it'll go down to 0.3 AU. But what you can see, I think then the deficit for the average width for the strahl doesn't actually seem to vary that much as a function of distance, but the deficit width does drop. You see deficits pretty. I think this is my last slide. I think. The deficit's pretty much constant rate throughout the time. Maybe the strahl is stronger in the mid region. I think the interesting thing about the deficits is that from Parker Solar Probe, the report is that you see them in the very inner heliosphere, but not much outside. So I think the fact that these are much more sporadic than the actual observations tells you that there must be some kind of special kind of solar wind that gives you these deficits. But you need to think about that a bit more, perhaps. Okay, so my last slide then, just to conclude. So I've looked at the occurrence rates and the characteristics of this very sort of simple analysis of the electron pitch angle distributions for just this fairly limited few months at the beginning of the year. Simple classification system. That if I use that, I see strahl beams in all solar wind speeds, but slightly higher, slightly more prevalent at high speed. You don't see a significant evolution with distance, so I think that shows this balance between focus and scattering processes. But you know, there are some results that the beam broadens with increasing field strength and narrows with solar wind speed. And then just a little bit here about these deficits, which we see in these sporadic clusters. Again, we see them across the distant range, although they occur in very sort of narrow time windows and therefore space windows. And it looks like, you know, the way they evolve, they are also influenced by some kind of scattering and defocusing processes. And if you're interested in looking at that in some more detail, I did manage to get this published a few months ago in Universe. Thank you very much for listening.
Show us again the definition of the quantity, the F hat quantity that you're plotting?
Yeah, so by this I just mean that this is the average phase space density in this pitch angle range.
Okay, but it's not, and that would be different from the integrated phase space density in those ranges, is that right? There was the part near the poles has less area, so you're looking at the total flux or the density?
So the distribution that I derive looks something like this. It's correct that the bit nearer the 0 and 180 degree pitch angle has less measurements associated with it, but that's taken into consideration here at this point. And then my categorization scheme just says, so what's the average flux there compared to the average flux here, and then compared to the average flux here. So it's you could do things more sophisticated if you like, but that was just a categorization.
If the distribution were isotropic, then it would be flat in cosine theta, right? Cosine of pitch angle.
I think that's already, it will be flat here, right? I think that's already taken into consideration when I move from 3D to this 1D kind of cut thing.
Okay.
I think.
I'm just raising the question.
Yeah,
it's
yeah.
something that people get confused on. It would be nice to be sure that we know which one it is.
Yeah, so.
We can talk about that later.
Yeah.
Technical point.
So I mean, to create these plots, then there are many, around the 90 degrees, there are many, kind of the solid angle, if you like, that you sampled is big. And the solid angle you sample at this point is small. But the balance has already been taken into consideration when I do these plots. So an isotropic distribution will be flat in pitch angle, not cosine. But I mean, I guess you could put it the other way around.
Okay.
Okay. Who was next?
I have two questions, one from Shadin, one from Lorenzo, and then we are done.
Okay, just quickly, this is an interesting plot. The flux is look, sorry. No, just an interesting plot because the flux seems to be variable during these 6 hours, very variable all across the pitch angles. So, I mean, it's you know, at 1AU it's slightly different.
Sorry?
At 1AU it's a bit more.
So I think this one was at
0.7, okay.
this particular example. But I think it is quite variable.
I mean, I'm surprised. I mean, just, you know, there's some parts the green is all over the place, and some part, you know, you have blue and.
Where it's green everywhere, it's more like quasi-isotropic.
Okay.
Okay, so a question and a comment. The question is whether when you looked at the dependence on parameters, you considered also some estimate of collisionality. So if
No, I haven't looked at that
but
specifically.
could be.
Yep, okay.
And the comment is that, okay, so to the extent whether as far as this the shape of the strahl is the result of focusing and potentially collisions, there is modeling which is being doing on that by also the local group here in Florence, especially Simone Landi. So you may want to talk to him because they can, for example, run simulation where varying the collisionality and the density or the speed, you can recover narrower or wider strahls as a function of distance, and so you can try to disentangle global effect and local effect.
Yeah, so I think I'm not sure whether I got there, but that was certainly the intent of this, was to try to do these processes, change their balance at different radial distances, for example, or for different types of solar wind. So yeah, for sure, talking to people.
That's the modeling that Laura was doing.
Yeah. Yeah.
Good.
Okay, let's thank the speaker again, and we will move to the next one. Thank you very much. So, the next speaker is Benjamin Alterman, and he will be talking about iron eating across a shock observed by solar orbiter heavy ion sensor, if I interpret correctly the FE acronym in the title. So, okay, you have 15 minutes plus 5 of questions. We are being a bit elastic in the first session because a talk was cancelled, but let's try to keep with time, okay?
Good morning. All right, fantastic. So I'm going to talk about iron heating across a shock observed by solar orbiter, the heavy ion sensor. This is work done with the heavy ion sensor team. So myself, Stefano Livi, Sue Lepri, Jim Raines, Ryan Dewey, Sarah Spitzer, along with the MAG and PASS teams. And of course, Chris and the Electron team. I'm going to tell you a little bit about HISS. We'll look at the shock. I'll summarize the heavy ion observations up and downstream. We'll talk about data selection and data aggregation. We'll then look at the iron VDFs, the extracted speeds and temperatures, and some mass per charge dependent heating. The heavy ion sensor is a time of flight mass spectrometer. It measures the energy per charge, total energy and time of flight of incoming ion. The teams supporting the instrument are from Southwest Research, University of Michigan, UNH, IRAP, NASA Goddard, Bern, and MSSL. As Chris said, we are part of the SWA suite. The thing that, if you take one thing about HISS away from this and how the instrument works, it is designed to achieve in 5 minutes what it takes SWICs 2 hours to get. That means we can go and look at the radial evolution of wind features, including stream interaction regions, CMEs, and shocks, and actually see very sharp boundaries. This higher time resolution lets us look at small-scale structures in the solar wind, and when we are able to provide 3D distributions, we'll be able to examine temperature anisotropies and heating in very nuanced ways. HISS is, as I said, selects the incoming ions based on energy per charge with the entrance aperture system. Looking at the composition in the room, I'm just going to tell you that we work, we get the data. I'm going to move on. I think that this is a little bit past where we're going to be. What you want to know is that we collect 29 azimuths and 15 elevations from minus 28 to 67 degrees in azimuth and minus 20 to 16 degrees in elevation. We have 64 energy per charge steps. These cover about a half to 75 keV per E. And we provide data at 3 different time resolutions. Notionally, we have a low cadence data set at 300 seconds, which we've actually never had to take because telemetry allocations are so high. Our nominal data is at 30-second time resolution, and we provide burst data at 4 seconds. We have provided an initial data release. I know people have been asking about when this was going to happen. It's available at the SOAR. We've aggregated to 10-minute resolution, and it starts in January of 2022, so this year. We had some noise problems and operational challenges prior to this date, If there's something specific you need, you can come and ask us, but our focus is starting from January moving forward. The provided level 3 data uses maximum likelihood estimation to separate overlapping ions. This has been used with a SWIX quite successfully. The data has quality filtering applied, and we are working to provide a fuller data set that includes more charge states, more abundances, and 3D VDFs. Currently what's available is the iron to oxygen ratio, along with 3 charge states, O7 to O6, C6 to C5, and C6 to C4. We provide an average oxygen and carbon charge state, along with normalized charge state distributions for carbon, oxygen, and iron, along with speed and temperature for O6. On March 11, 2022, solar orbiter was about 0.44 AU and inbound towards perihelion, and we observed a shock at about 1952. It was quasi-parallel. The shock speed was about 724 kilometers per second. And you can look here if you're particularly interested in this shock. You've got the parameters here for how it was behaving. On the top panel, we've got the magnetic field components. We've performed a wavelet transform on the data in the second panel, which we'll go into in a minute. Got the alphane speed and theta BN on the next panel, along with the velocity components. The shock occurred here. What we've done is we've used the wavelet transform to identify times when either the magnetic field was, we're going to call it steady-ish, or when there was a lot of wave power, and tried to isolate those periods to specific intervals and aggregate only either when the magnetic field was stable or right around these high power intervals. So that way we're looking at VDFs that are aggregated sufficiently to provide statistical certainty, but not smearing out the features across different measurements. Those intervals are from each of these little pink tick marks to the next, so they are variable in size. When we move forward in this, we're going to look at 4 examples, 1, 2, 3, 4. We've got basically an upstream VDF, a VDF that we think is in approximately the 4th shock, one directly at the shock, and then one downstream. In this case, we're doing this work in part to look at later data releases, so revisions to our L3 data release. So we're going to do RIN selection not with a maximum likelihood estimator, but looking at energy per charge time of flight tracks. I'm showing here 30 minutes upstream and downstream of the shock. Part of why we do this is it enables custom time aggregation for our higher level products. What we see comparing these two things is you can see the shift from an energy per charge of around a coupled to an energy per charge here of around 10, where these red centroids increase in energy. That's just the change in solar wind speed across the shock. You also see heating, where the distributions broaden across the shock. The different tracks overlaid are different ions, really they're different mass per charge values, starting with protons and then alpha particles, O6. And then those purple tracks are irons 12 through 7. We're going to be using irons 12 through 8. When we go through and do our aggregation at the time interval specified with those orange ticks at the bottom of that top panel, you end up with an energy per charge spectrogram that looks like this. In this case, this is iron 9. We can see here the increase in both speed and temperature across the shock. This particular interval, let's see. So the time period here corresponds to the left edge of that plot, and this is the right edge of the top panel. So to perform the fitting, what we've done is we've taken all of these charge states, all 5 of them. We select the center part of the VDF for fitting and fit a 1D distribution in the plasma frame. We move from the upstream to the downstream from top to bottom. So upstream for shock, at the shock, and then downstream. We're only showing irons 8, 10, and 12 just for space. In these panels, the dashed histogram values are all of the data we have. The solid values are the central ones we've selected for fitting, and then the dashed dotted lines are obviously the fits. we've got here are all 5 charge states of iron that we're looking at. The top panel is the speed, followed by the differential flow normalized by the alphane speed, and the thermal speeds on the bottom. You see a consistent speed for all iron distributions, both upstream and downstream, and they tend to track each other across the shock. Across the shock, there's not much of a change in, there's actually about a 50% change, in the normalized differential flow. And then as the thermal speeds spread out across the shock, you start to see different behaviors for different charge states. How does this change in thermal behavior actually look as a function of time? Instead of plotting each distribution as a function of time or the parameters as a function of time, we're going to plot the temperatures as a function of mass per charge and look at how the mass per charge dependent heating changes across the shock. We've got here on the left is the temperature at each time interval given in color as a function of mass per charge, and we can then fit these trends and plot those slopes here. Up to the shock, we see that there's basically no real heating. The temperatures are constant as a function of mass per charge. We hit the shock, and then that slope becomes markedly steeper and stays so further and further downstream. These observations provide us with an initial ability to actually see that discontinuity and see how that heating changes as that shock crosses the spacecraft. One of the things that we're looking to do with this is potentially back out things like the theta Bn across the shock and to understand how you can see different mass per charge dependent heating based on the shock geometry. So there are a couple of things I wanted to point out to you about this. We've taken iron at VDFs down to 2-minute time resolution. The variable time aggregation allows us to look for variable time intervals that provide steady state observations of iron at up to an order of magnitude faster than you'll see with ACE-SWIX. We've got velocities and temperatures, and we've seen mass per charge dependent heating. I was expecting us to be a lot later and have another 2 talks this morning, so I went short. Yeah. Right. I was expecting 2 more talks and to be late, so. Questions?
We'll blame this on Marco Velli, who's not here today. Questions?
Hello, thank you. I didn't catch it and I may have missed it. What is the Mach number of this shock?
3.27.
So it is supercritical.
Yes.
And so the ions must be resonating with waves to become heated.
What I haven't shown you, what I haven't shown you is really high time resolution magnetic field data, because this shock is actually very interesting and strange. So let's just say I'm not comfortable saying it's just that.
What I'm interested in is how the waves are amplified as you go across the shock, and I'm wondering whether you can ultimately get some handle on that.
It's not that clean looking at the high time. Like it's just not that clean looking at like the really high time resolution magnetic field data.
Anyway, very nice. Thank you.
Yeah.
My question is related to that question also, that I would like to ask you that, have you seen any amplification of the waves in the foreshock region, if there is any such thing as foreshock or accelerated particles energy? Because this is a quasi-parallel shock, I guess.
Haven't gotten there yet.
Okay, thank you.
Hi, no, just a quick comment. About the next steps, of course, we are going to explore also the heating of heavy ions as a function of theta Bn, but I also believe that it would be very interesting to explore this as a function of the sonic and alphenic Mach number, the magnetosonic Mach number, because this, of course, will be affecting, I mean, the interaction of the shock also with the turbulence pre-existing upstream.
That's when we have multiple shocks. This is for just the first case.
Yeah, okay, but very interesting work. Thank you.
Are there any other questions? Oh.
Just a quick one. Why do you use iron? I mean, there are other heavy ions where you have a lot more from, right? I mean, you could, if you do this with oxygen, you could probably get the errors down, right?
That's because this was a really strange interval. This was a really intense shock. So to protect the instrument, we have a couple of different things that we do to make sure that we don't damage any of the internal components. One of which is we, for example, don't go to low energy per charge at times of high flux. That's called our proton avoidance. In this case, not only did it cut off protons, the shock was so intense we cut off some oxygen and some alpha particles. We also had such high count rates that we were starting to saturate in some of the ranges of our telemetry. Like, so because of the number of counts we get in telemetry limitations, we have to specify what subset of this parameter space we bring down, and we take down a fraction of it depending on where you are and what's important. And it turns out we also saturated a bunch of stuff there for other things. So a part of why we chose iron for this is we got it. We don't have the other stuff, so next time.
It makes the future even more complicated, right? Because then you not just like waves, angles, Mach numbers, but also a whole bunch of ions, right?
Yeah, well, absolutely. On the flip side of this, we could also say that what we're seeing here is we can see just the importance of the charge state without combining in the mass variation. And if you were to look at something like where you have to assume a charge state even for an average charge state over some time interval from, for example, the von Steger papers, here we're telling you for a specific charge state for a single element, how does that behave?
Are there any other questions? Okay, we have one from Bill.
And could you put up the stacked plot of the different time series?
Which one? This one or the light?
That'll work. So, yeah, what is that other discontinuity or near discontinuity in the magnetic field strength that happens later around 2012?
Possibly another shock. We're not entirely sure. We're looking into what that structure is. There was a lot going on here. It's possible that we had two shocks running into each other effectively.
Okay.
Any other questions? No. Okay, so if that's not the case, I guess we will thank the speaker for 8 minutes because no. So just before we go to the coffee break, I just want to remind you so that this is an exceptional, to make an exception for all the people that many people couldn't come at the end and canceled, we made available a streaming on YouTube for a passive stream for people to follow, and this will be a one-time thing for this workshop probably. But if anybody of you wouldn't feel comfortable to, because this is a very informal meeting, we are presenting partial result and discussing. If anybody of you wouldn't feel comfortable in showing this result and streaming on, you can simply deactivate the streaming from here with one button or ask me to do it, and I will do it during your presentation, okay? No problem. Now I guess we have our coffee break slightly 7 minutes in advance, and we reconvene here at 11:20.
però sì, sì.
Ma più o meno in che zona della città sta?
Io abito vicino all'aeroporto di Ciampino.
Ah, ok, allora stai vicino a lui.
Sì, quando non
sì,
c'è
lo so,
traffico
sì,
un quarto d'ora sei in sì. Ieri c'è
Io passo da mio fratello che vive a Roma, quindi quando vengo si compra il 50% della vita. E lui sta in cielo.
Ed è un casino.
40 km al giorno per venire in macchina.
Guarda, mio marito lavora a Castello.
Appunto. Io faccio il contrario.
Dove vai scooter? Si può fare. Sì, anche con
A 3 ruote. Ah, però sono belli quelli a 3 ruote. Ok. Proverò a usare la campana per i 3 minuti. Proverò questa innovazione tecnica. Ok. Okay, everybody's back. So we resume our session, and now we have Denise Perrone, who will talk about radial evolution of magnetic coherent structures in the inner heliosphere, PSP and solar orbiter observations. So now, from now on, we really try to be strict. So 15 plus 5 minutes of question. You are welcome if the speakers allows you to ask questions during the talk. And please.
Yeah, absolutely. You can just interrupt me, ask me wherever. Okay, thank you very much. So, okay, I will try to move faster since I have just 15 minutes. So this is the outline of the presentation. Can you hear me well? If I wear my mask? Okay. So I will try to describe some in situ observation in the inner heliosphere of this new data set of particle solar probe and solar orbiter, discussing this non-adiabatic expansion of the solar wind, moving to coherent structures, and then some features, non-Maxwellian features on the particle distribution function. So this is just like advertisement. So we are really living like in a golden era for the inner heliosphere physics and solar physics, having this new mission, Parker Solar Probe, launched in 2018 and Solar Orbiter launched in 2020. But we cannot forget the past, because that mission are not the only mission that started to measure solar wind in the inner heliosphere, but we have this very old twins mission, Helios 1 and Helios 2, that was launched in 1976, and they give the first 3D particle distribution function in the inner heliosphere, and the big pointer is here. So, okay, so here is just an example of the ion distribution function. This is the part of the core. This is the alpha particle that is in the radial directions. What is clear from the observation is the beam along the magnetic field, and we have a very strong temperature anisotropy in the direction perpendicular to the magnetic field. And thanks to the Helios mission, we had the first study of the heliocentric variation of the solar wind in the inner heliosphere. Usually, this kind of analysis has been done using the velocity as a threshold to separate the fast solar wind from the slow solar wind. But doing this, usually we can mix plasma coming from different sources, or like taking into account the interaction region that can increase also the statistic on the temperature, for example. So what we can do, usually the best thing that we can do is try to study some line-up between satellites in which two satellites can see the same parcel of the solar wind, but this is a very lucky event. Something else that we can do is try to study the radial evolution of plasma coming from the same sources on the sun. So we are not analyzing the same parcel, because it's not the same solar wind analyzed from the different satellites, but taking into account the sources. This is usually done for fast solar wind that is come from the corona holes. If the corona holes is stable, we can having the fast solar wind coming from these sources on different solar rotations. And here is just an example of 4 months of Helios data in the inner heliosphere. As you can see, the bottom panel is the radial distance from the sun, so it's going from the the Earth, and then to the perihelion here. And this is a minimum of the solar activity, and we can recognize fast and slow solar wind. And after 27 days, you can see that we still have the same fast wind. So it's not the same plasma, but coming from the same sources. And in this way, we can really analyze just a fast solar wind and study the radial evolution, just removing or at least reducing an additional external effects, mixing sources and something like that. So using 1.5 years of data of Helios mission, I studied 3 different sources on the sun, so 3 different recurrent fast wind that here in the table are indicated by different letters. So in this the C, and then for the A we have 9 different streams at different radial distance. And here I put just some example for density and temperature for the radial evolution. So the different colors are the different sources as in the legend, and you can see here is the black line is the fit. This is the first point for Parker Solar Probe, not the real one, but just an extrapolation during the first perihelion if Parker Solar Probe was looking for a fast stream. So in the fit you see that the density is going down really as we expected for a radial expansion. The comparison with the dashed line is for the work for Petre in 2011, in which he used the moments of the distribution functions, if I'm correct, and also the velocity as a threshold. And you see there is a difference between the 2 analyses. This is just an example for the temperature. So we see that the adiabatic prediction is in red, and we see that the temperature is going down slower with respect to the adiabatic prediction. But moving to new data set. So on the left panel, we have the first months of the solar orbiter missions. The top panel is the velocity of the solar wind. As you see here, we have a fast stream at the end of August, and then after more or less 1 solar rotation, we have another fast stream at the end of September. And looking at the longitude, solar orbiter passed more or less at the same longitude and was connected, so at the same corona holes, that is the sources of these 2 fast streams. So this is a recurrent fast stream. And then we are very lucky because in the same period, during perihelion, Parker Solar Probe at more or less 0.1 AU was connected to the same corona hole. So we have a privileged point of view at very close distance from the sun, because for solar orbiter, the distance is around 0.91 AU, so it's not really inside the inner heliosphere. So here are the example of the streams. So the first panel, is the magnetic field, the 3 components. Then there is the velocity. This is the angle between the velocity and magnetic field, density, temperature, and plasma beta. What we analyzed for this works was what is highlighted by this green shadow. As you see, for Parker Solar Probe, this is the period of fast wind that we observed, and we collected all these data sets. You can see that for the velocity, for the particle measurements, the fluctuations are very high. This is due to the fact that it is close to the sun, but also from some field of view problem of the SPAN-I instruments. And then for solar orbiter, we decided to don't take all the interval of fast wind, but we decided to take just intervals in which, for example, the plasma beta is almost constant, just because we don't know what will happen here, because there are strong magnetic field change, for example. So on the right side we have the averaged values for these intervals. In the bottom table we have the fitting for the radial profile of different quantities, just to see what is going on for density, magnetic field, temperature, plasma beta, that is in agreement on what people already found using previous data sets. And here are fluctuation, or better are the components for magnetic and velocity field normalized to the mean magnetic field in the whole interval. As you see, there are a strong correlation between magnetic field and velocity fields. And taking into account that we have also almost constant magnetic field and density, we can say that this interval are strong alphenics. What else? Okay, here is just the turbulence analysis, the classical one. So that are the spectra on the left side for the magnetic field and on the right side for the velocity fields. Since the resolution of the measurements, we can see that for the magnetic field, we can cover also the dissipative range that we cannot reach by the velocity fields measurements. Clearly, we have that the power law is decreasing, going from the measurement close to the sun to the one close to the Earth. And also, for what concerns the spectral break is moving to lower frequency as the wind expands in the inner heliosphere. And if we take into account the slope of the power law, for the magnetic field is between the Kolmogorov and the Kriknam scaling that is moving from the Kriknam to the Kolmogorov one, and for the part relative to the dissipative range, we have also a steepening of the spectra. And for what concerns the velocity fields, we have that the scaling is really close to the Kriknam one. It's not changing in the limit of the error, changing the radial distance of the three streams. Okay, so here are the normalized magnetic energy for the three streams. As you see, the distribution is not uniform, but we can recognize some localized events in times. These red lines elongated from large to smaller scale that have also strong phase coherence between scales that are not shown here. So we can call it coherent structure, so better intermittent events. And in order to analyze what happens along the spectral break, we reconstruct the magnetic fluctuation around the ion break that are difference between what Parker Solar Probe observed and what solar orbiter close to the Earth observed. And this is the formula for the reconstruction. And what we observe is that the distribution of these, yes? The formula. So this is the reconstruction of the, is like a bandpass filter for the magnetic fluctuation done with the wavelets. So this is our parameters for like time. This is for just for the construction. It's for the Morlet function that I used. This is the real part of the coefficient for the magnetic fields fluctuations, a component. This is just the time, the relative time for the. Okay, so no, okay. So this is the distribution of the parallel component, for example, in this case of the fluctuation, the magnetic field fluctuation, the reconstructed one. So you see that are not Gaussian, but we have the EV tails. This is an indication, again, that we have strong events, strong energetic events. And here is just an example of what we define as we define strong events. So this is a threshold that we have, this line that corresponds to the 3 sigma of the Gaussian distribution function. And we pick up these points and we look what happened there. And what we see is that we have a very clear profile for these fluctuations that are localized in time. So this is an example. Yes, Luca, sorry.
Was it PDF taken over the whole interval filter?
Yes. No, this is just for all for the reconstructed, the one in the period that I showed before in the spectrum. Yeah. Okay, these are examples of fluctuations of structures that we observed. In that case, is in a previous work that I did, and is for the first perihelion of Parker Solar Probe. So in the inner heliosphere, what we observe are in fast wind. In this case, was slow alphenic, let's say alphenic wind. We have something that we call the current sheet, so some magnetic coherence structures that have a strong rotation of the magnetic field. The two panels in the bottom are the fluctuations in the minimum variance reference frame. This is in the local magnetic field frames. Then we have something that remember as some kind of vortex, so very with a few oscillations, and it's more or less a 2D component structures. And this is more or less like a packet of waves that in the analysis we recognize as ion cyclotron waves. And this is the analysis for the three streams that I showed before. So this is just a statistical analysis. All the histogram here are normalized to the number of events that we found. So we need to take, to do a consideration in that case. 5 minutes, less? 3 minutes. Okay, I just finished. Anyway, so the length of the intervals that we consider are very different, because for solar orbit is around from 5 to 7 hours, and from Parker Solar Probe is like less than 2 hours. But the number of structures that we found in these intervals are like in the Parker Solar Probe double number of events with respect to the one for solar orbiter. But we need to consider that also the characteristics scales of the structures are different, because in Parker Solar Probe are much, much smaller. So if we try to do a normalized time scale, or better length for the intervals, we expect to have more coherent structures in the intervals for observed close to the sun with respect to the one close to the Earth. And that's exactly what we found. And here just very quickly, this is the analysis for the minimum variance frame for all the structure that we have. What is important is the angle between the maximum variation of the fluctuation with respect to the local magnetic field that are more or less perpendicular. And this is just to say that is well resolved, more or less well resolved, the minimum variance analysis. And here is for what we have for the beta, the plasma beta. This is for the one for Parker Solar Probe, that is around 0.5, and for solar orbiter it is more around 1.7. And this is what we also observed for the wall interval. So it's, remember, what we have for the from the beginning. This is the angle between the B and V in each structures, and we have that for Parker Solar Probe is more or less peaked around 40, and for Parker Solar Probe here it looks like it's more constant between 40 and 90. And this is a parameter that measures the compressibility for the magnetic field. So in fast intervals that are strong alphenic, we don't expect to have too much compressibility for the magnetic field, and it's what we found also for the structures. But going from the sun to the Earth, the peak of this distribution is going a bit on the right side. So the compressibility starts to increase as we expected during the expansion of the wind. And here is just two examples for current sheet that we observed in Parker Solar Probe and Solar Orbiter. It's not the same structures, it just belong the same families of structures. And what is very interesting is that if we normalize the width of these structures, if we assume that it's just convected from the wind, and taking into account the normalized length with the characteristic scales, we see that the width of the structures is more or less the same. So also if we observe at two very different radial distance, the main properties of the structures look like similar. And this is an example of vortex-like structures at the two radial distances. And what is very important is to look what happens on the particles close to these structures, but unfortunately the resolution of the particle measurement are not enough to study this. Here I put an example for cluster measurement on the left and the MMS on the right on what we already found in different analyses close to the current sheet, close to the vortices. And okay, this is the summer, and I can stop here. Thank you.
Time for 2 questions. I will start with Andrea, because I decide.
Thank you, Denise. It's
Thank
very
you.
interesting.
Thank you.
I'm more interested in the large-scale part of the
Yes.
data analysis. Have you looked at the Alsace field spectra? Because it looks like a weird radial evolution and could be interesting
Yes,
to...
so we have a problem here, especially for Parker Solar Probe, because the field of view noise that we have for this analysis is very high. So due to the Alsace variable will be a bit difficult.
At least for the dominant one.
Yeah, yes, but it's even worse at 0.1.
Just a second question,
yes.
quick one. So since it's, you showed before that you basically recover the radial evolution of temperature as 1/r. Have you looked at the energy content in fluctuations in this interval and how it fits with this kind of turbulent heating?
Not yet, but it's something that we are doing in ongoing project. Thank you.
Very interesting material, Denise. Thanks. All of the analyses that you did in the latter part of the talk were based on looking at this band pass analysis.
Yes.
How close were how large is that band in
it's like
time scales?
It's like 1 decade in frequency. So it's between 0.1 and 1 hertz, more or less 1 to 10 hertz for the Parker Solar Probe.
A lot of those statistics that you looked at can also be done with increments, right?
Yes, sure.
Have you taken any of your basic results and done them with increments just to compare?
We are doing this analysis now with Sylvia. Yes, we are trying to compare now with the PVI, for example. Try to look what is going on, if the statistic is comparable on what we observe.
A related question is the spectra that you showed, where you looked at the various spectral slopes, like here.
Yes.
Are these all? These are not wavelet spectra. These are FFT.
This is FFT spectrum. Yes.
Which?
FFT spectrum.
FFT.
Yes.
Do you ever check these against spectra computed from Blackman-Tukey analysis?
No.
Correlation analysis?
No, we didn't. We didn't. But
particularly in places where the spectrum becomes steep at some point, they can differ.
Okay, thank you very much for the suggestion. We can try to do it. Thank you. Thank you.
Okay, let's thank the speaker again. And now we'll move to the next speaker, who is Simone Opie, who will be talking about turbulence and instabilities in the solar wind, an investigation of scale-dependent processes using solar orbiter data.
I don't know why this is so small. Let's try that, see if it...
Okay.
Okay.
I will bring that, we have 3 minutes left.
You're ringing the bell? For me? Okay. So I'm going to get the bell rung. Hello, good morning still, everybody. I'm a PhD student, and these are my collaborators who I'm working with. I'm working at MSSL as part of UCL, and I guess you could say I'm probably a living data point for the proposition that appearances can sometimes be misleading. Okay, so I've been working on data from the Solar Orbiter mission, and I'm just going to run through some outputs from the research that we've done. About half of them have been published. The other half are in preparation at the moment and shortly to be submitted. And then there's one at the end that, if I have time, I'll try and squeeze in. So the first thing is this is the data set. So it's a statistical analysis. I'm using about 1 million data points from the Solar Orbiter mission, mostly in the cruise phase. And you can see, sorry, I don't know what's happened there. I haven't got a yeah, no, I get rid of, oh, it's not on your screen. Sorry, it's only on my screen. It's prompting me for eduroam. So what you can see here is the plot of the data in temperature and anisotropy beta space. And one of the things that's of most interest working at the resolution, the 4-second resolution of the PASS instrument, is that we see quite a lot of data in the unstable regions. And so that's an opportunity for kind of understanding the roles and conditions of instabilities in the real solar wind.
So are these ions or electrons?
Ions, yes. Protons. Essentially protons, yes. Sorry, I can't move it on because I've got a Wi-Fi notice on, so I'm just going to have to try and escape from that. Right. Okay. So the first thing that we've done is to look at the angular distribution of the instabilities relative to the stable data. So we calculated a three-dimensional angle between the bulk velocity of the solar wind and the magnetic field. And you can see from left to right, we have on the left-hand side the stable data with in fact the all data set, which is in blue just behind it. We have the oblique fire hose unstable, which is in green, and mirror mode unstable in magenta. The three-dimensional angle for these plots is projected conformally onto the two-dimensional plane. And what we see here is that there's an angular dependence for the instabilities. And this angular dependence, which shows that for the mirror mode on the right, these occur when the magnetic field and the solar wind bulk velocity vector are more or less quasi-parallel, and for the oblique fire hose we're quasi-perpendicular. And in fact, this arrangement is the exact opposite of what we might expect from CGL double adiabatic expansion. So we see quite a clear angular dependency. And what we then wanted to look at is how this relates to the persistence of these unstable intervals in the plasma and in the data set. So we calculate for each interval the aggregate length scale associated with that interval. So we take each consecutive data point, we calculate a length scale, which is in fact in gyro radii, and we aggregate those to give us a combined length scale for each unstable interval. And we then look at those both for mirror mode and for the oblique fire hose separately. And when we do that, what we see is the following. We see these plots where we have essentially a breakpoint, which is in a different place for each of the instabilities. But we have a breakpoint which, beyond which the instabilities are acting to diminish the number of points that are residing in the unstable intervals. But up until the breakpoint, we basically have a kind of static distribution. And we identify length scales with those breakpoints and you can see on the left-hand side of 34 gyroradii and on the right-hand side 24 gyroradii. And in fact, the power law decline after those breakpoints is pretty consistent between the two data sets. And so we characterize this. What we suggest is that these breakpoints categorize intervals where the instabilities are in fact growing to the point where they are then acting to reduce the unstable data distribution. And so in terms of this first phase of the work, here are some of the sort of key points. We have unstable intervals of a length of at least 10 to the 3 kilometers are needed for these instabilities to act. In terms of the instrumentation, a sampling cadence of less than 10 seconds is needed to observe the full length scale distribution of the unstable intervals in the solar wind. And then we use an estimate for the maximum growth rate of k rho equal to 0.5. And we're able to calculate that this minimum space that we've identified for the instabilities to act is around approximately 3 wavelengths for the oblique fire hose and 2 wavelengths for the mirror mode. So we then move on to look at the impact of the variability in the magnetic field on the instabilities themselves. And we developed a measure which is essentially the standard deviation for the data packets that relate to the magnetic field for each of our data points in the past data set. Sorry for the interruption. And what this allows us to do is we aggregate 32 measurements from the magnetometer and assign those to each of the past measurements. And those 32 measurements are spread around a 4-second interval around each of the 1-second sampling intervals that the past instrument takes. And we start by normalizing the data set to give us unit vectors so that we are in effect eliminating the compressive fluctuations from what we see. And when we look at that, as you see on the next slide, we overlay that into anisotropy beta parameter space, and we also plot the PDFs on the right-hand side. What we see is that this increased fluctuation is associated with the thresholds potentially in the parameter space. And further on the right-hand side, what we can see is that for the instabilities, the distribution of the variability has a cutoff at a higher level than for the stable data, and what's more, the distributions are biased slightly to higher values than the stable data set. Yes, yes, it is. It's calculated as per. Sorry, I don't know why this is doing this. It's calculated as per that previous slide. and so as you go up the color scale, you're getting increased variability. And you can see that the increased variability tends to cluster around the oblique fires and the mirror mode thresholds, although it also has quite a clear dependency on beta as well.
How much of this is just, how much of this is just the thermal pressure becoming dominant at higher beta? Because I would expect to see more variation in magnetic field's direction as the thermal pressure just takes over in terms of dynamics.
Well, there clearly is some relationship there. However, the variation that we're looking at is the non-compressive variation. So we think that what we see is a real signal, although I agree there is a beta dependency in there as well. Yes.
Yeah, and so velocity eventually. So it's hidden in there. I think this kind of correlation we always see in solar wind.
Yes, and I'm not saying there aren't other correlations in there. What I'm specifically looking at is, well, what are the characteristics that relate specifically to the instabilities and the thresholds? Yes, it is. Yeah. No, absolutely. That's clear. But equally, well, I'll show you some other things, but there's stable data in that region too, and there's a distinct difference in the variability between the unstable regions and the stable regions, even at the same value of beta. So it's not just a beta dependency. What I'm looking at is the difference between the blue line and the green and the orange line, and I do see that there is a difference. And if we go to the next slide, where I've overlaid that onto the angular distributions, what you see is that for the instabilities, they have a higher threshold in terms of the variability than the stable data, which is the plot at the bottom. And what's the axis of the y-axis? The y-axis is this sigma b, which is our measure of variability in the magnetic field. It's dimensions, because it's the standard deviation of the data set. So it's basically measuring the flips in all three directions, aggregated across, and then we take the square root of the squares of each one. And what you also see in that PDF, in the two PDFs, is that the unstable data, the clusters around these local minima. So you have this minimum threshold at which you see data in the unstable regions, and those levels are higher than for the stable data set. And so we go one step further with this, which is that we then plot in parameter space for the for the sigma b versus the length scale versus these same persistence intervals for the unstable data. And what we see clearly here is that as the length scales increase, we see that the variability of the magnetic field in terms of these alphanic fluctuations decreases. And further, we see this sharp cutoff at the bottom, beyond which we don't see any unstable data, whereas we do see stable data for the exact same conditions in the anisotropy beta space. And so we infer that the instabilities act directly to reduce the fluctuations in the background magnetic field. And that's sort of an interesting result that coincides with some thinking that, for example, Shikochin and Matthaeus have written about and have provided analytical frameworks for, but we're looking at it from an observational data point of view. I'm going to have to skip my last little bit, which is fine. So I'll just skip on, which is a shame, but there you go. So I'll skip on to the summary of the results. We quantified the angular and length scale dependencies of the oblique fibers and mirror mode instabilities. We develop a measure for these non-compressive fluctuations. We did, as it happens, also develop a measure for the compressive fluctuations, and qualitatively they're similar, although in fact fluctuations, the measure is lower by about a factor of 5. Sorry. Right. I won't talk about the fractal dimension. That's the bit I've had to skip over. And we demonstrate essentially the kinetic scale instabilities directly influence background turbulence. And just to clarify that, those are the two plots I showed earlier. That plot on the right-hand side is for the stable data. So that is by synthesizing all of the possible length scales that I can derive from stable data. And what we see is that the distribution in that plot on the right is pretty much completely flat. So I'm afraid that's all I've got time for, but thank you very much for listening.
One question. Anybody else? She already had a question, so if no, okay.
I have a lot of questions. I'm sorry. No, just I'm a little bit lost. You're speaking about non-compressible things, but then mirror modes are compressible. Then you get for mirror instability the θ/BV angle 0, but the wave vector of mirror instability is perpendicular. And then, so I'm a little bit lost.
Okay, so the reason why we chose to look at the non-compressible measurement of the fluctuations is that when we get to the point of looking at the threshold, it has been interpreted when you see that variability increasing, that those are the fluctuations generated directly by the instabilities. So what we wanted to do was to, in a way, remove those from the picture. So we've concentrated specifically to exclude the compressive fluctuations, so that the action of the instabilities themselves is less influential on the result. It's not completely removed, but
Let's discuss it later because, yeah. And then this fractional dimension seems to be very interesting. Maybe we can allow to show this slide.
All right.
Yeah. Yeah, please.
You want to see the slide?
Yeah.
Okay. So there's the slide. There's a little bit of preamble, but essentially what I've done is extend the variability measure across a number of different time scales. So I've scaled it up and I've used the result of that as a way of calculating the fractal dimension. And what you see is that between those blue cyan, between the cyan lines, between 2.5 and 2.7 those are the limits that in the Mandelbrot literature for what he calls curdling, which is essentially homogeneous intermittency, and we see that up until a certain time scale, sketched in also the sort of long-term correlation length of the turbulence, we see that the stable data sits pretty much within that, whereas the unstable data is in a region where perhaps one might consider that the turbulence is space filling. It has this higher fractal dimension. But that's there's more work to be done on that, and I need to take that further.
Okay, let's fastly thank the speaker again and we welcome the next speaker. I point out that I take into account the interruption in the 15 minutes. I'm not giving him less time. So, next speaker is Giuseppe Nisticò, who is going to talk about dynamics of comet tails in the solar corona.
Thank you.
Come facciamo a cambiare la modalità? No, perché prende questo come schermo, invece questo è lo schermo di posizione.
Prova a fare poi fai il mirror screen invece.
Ah, sì. Displays.
Fai il mirror display se vuoi.
No, perché questo è difficile. Grazie. Non funzionava. Come funzionava?
Puoi dire fai presentazioni sullo secondo schermo forse, sul coso.
Slide show.
Present view.
Come se fa così qua? No.
Questo non c'è niente. No, fai mirror display settings.
Aspetta. No.
C'è qualcuno che sa usare un Mac che io... deve invertire due schermi.
Sì, sì, un PowerPoint.
Cavolo, quindi no, nel senso,
Hai messo il fai la visione. No, ma gli devi dire a lui qual è lo schermo principale, se no fai il mirror del display.
infatti, però sto cercando di come fare il mirror, ma non lo
Il
vedo.
mirror si dovrebbe fare.
Scusa. Scusa. Vai, fate voi.
Display preferences. Che sarebbe questo? Vai. Se no aspetta, forse se la metto qui la presentazione su questo schermo, la trascino, potrebbe funzionare. Non
Use us. Clicca.
sì, no, extend.
Mirror built-in rating, vai, clicca così. Ok. Vai.
Penso di...
No, rifai la presentazione.
Ah, rifaccio la presentazione?
Swap display. Vai.
Se ti riesci.
Ok. Vai.
Infatti. Ok, good morning everyone. And today I'm going to talk about some work.
Silence, please. Thank you.
That is still in progress. This work is led by Alessandro Bemporad from Turin, and the involvement of different members from the METIS team. I'm also contributing to this topic about observation of comets in the heliosphere with the coronagraph and the heliospheric imagers. And in this talk I will present in more detail an observation of a synchronizing comet from the coronagraph of solar orbiter, the METIS coronagraph. So, why it's important to study comets? I mean, it's a very exotic topic. But comets actually are the first evidence of, from a historic point of view, of a flow from the sun, since are the tracer of the solar wind indeed. And the tails of comets is very dynamic. For example, here I show an example of the comet Henk observed from the heliospheric imager of stereo A in 2007 that interacts with the CME in the coronal shock, and you see the disconnection of the tail from the coma of the comet. So, and also there are some kind of very like dynamics, and they interact so with the solar wind medium. The length of this object, the length of the tail can be very up to several astronomical units, like in the case of very bright comets, like the Yakutak comet in 1996. And then also there is a small class of comets that they have a very closest perihelion to the sun. These are called the sun-grazing comets. So usually these are seen with the coronagraphs and enters in the field of view of different coronagraphs like LASCO, stereo, and also solar orbiter now. So how can we use these comets to probe the physical condition of the local environment? Essentially, the dynamics, what we can study is the dynamics of comet tail. We have two types of tails, ion tail, that here we have an example in this graph here, where the ion tail essentially is formed of ions that are picked up by the solar wind flow, and the direction of the tail doesn't follow directly the radial direction as the solar wind does, but also there is a combination with the orbital, with the speed, the orbital velocity of the comet around the sun. So if we put ourselves in the reference frame of the comet, we simply the direction is given by the vectorial composition between the direction of the solar wind and minus the velocity of the comet orbital speed, or the comet orbital velocity. So this determines the direction of the tail that will form with respect to the radial direction some angle that is also known as the aberration angle. The dust tail is a little bit more complex. It's formed from very tiny particles with the size of micrometers. And these are emitted at different times along the orbit when the comet, the nucleus of the core of the comet passes. And this essentially the motion of this dust is determined by two forces. One is the pressure, the radiation pressure forces that push the dust outwards, and then the gravitational force. The combination of these two forces gives this kind of shape for the dust tail that is also known as a Sindine tail. This is the name of this kind of curve that they make. And if the dust then it's charged, you can assume that it can be also charged. There can be an action of a Lorentz force because of the interaction with the interplanetary magnetic field, etc. And this was also observed study for some very bright comets with a very, very nice tail and very complex. So. Observation of a sun-grazing comet with the solar orbiter. Here now I present a movie with this, let's see if, where we have the field of view, a part of the field of view of Metis. This is the occulter. So this is just a base difference. So this bright spot is actually a star that is difference, and then you see the star that is moving away in the field of view. But you can recognize the bright comet, sun-grazing comet, that is this one, that moves from almost 15 solar radii to 10 solar radii and then disappears. And also this main object is preceded by two small fragments that maybe can be related or not by this main comet. So this is the main one, but you see first this fragment, this other one here. So, but we focus, of course, on this main event. So this is an object that belongs to the family, the Kreutzer family of sun-grazing comets, and the particularity or peculiarity of Metis is that we can observe the event in visible light, also in the Lyman alpha, in UV with the other channel. This event was also observed by other coronagraphers like LASCO and Stereo, and so in this way we can also study the shape of this of the tail in 3D by doing a geometric triangulation. These are the events observed by Stereo A. Here on the right, you see also this is the coulter. Okay, now it doesn't move and doesn't play anymore. Let's see if I can. Okay, this is LASCO, so you see the comet is there and moving, and then it disappears. And then in Stereo A, in the coronagraph core 2, is this one. Oh, sorry. Okay, you see this bright comet here. This is just a running difference of the core 2 images. So what we did is to use simultaneous observation from solar orbiter, from Metis, and from Stereo A. This is the constellation of the spacecraft at that time. So solar orbiter was almost at the aphelion, so very close to Earth. Stereo A is here, and so they observed the sun almost this was the trajectory of the comet that was reconstructed. So actually we got the ephemerides for this comet that this will be the trajectory in the heliocentric equatorial reference frame, where this is the sun, but the comet of course just reached some distance very close to the sun here. So by doing this, doing a geometric triangulation of simultaneous observations between Metis and core 2, we are able to reconstruct the tail in 3D. So what we did is to use some tool that is available in the solar software packages in ADL. And essentially this tool is the STCC measure procedure. It's just a widget that allows the user to define some type points that reconstruct some structure in corona, but also in this case it works for structure in the outer corona observed with the coronagraphs. On the left side here we have the view from Stereo core 2, and this is the view from Metis on solar orbiter. So actually, the observation is separated over 2 minutes almost, and also the observation are affected by the acquisition time that is different in both instruments. It's about some minutes for core 2, and the exposure time, or the acquisition time is not really the exposure time, for Metis is quite long, about 10 minutes. So you see that the coma of the comet is very blurred, it is very elongated along the motion of the object. So what we did is just to pick some points from the images in core 2. The software then allows to plot the line of sight of core 2 in the field of view of the other instruments. So the line of sight is just from here, it's just out of the plane of view, so perpendicular. This will be the line of sight of core 2 in the field of view of Metis. So the line of sight intersects the comet, so the object at some point. So we click on this object, and finally we are able to get to make a triangulation and to get this point, the 3 coordinates of this point. We did this for a sequence of 6 frames, and so we sampled the tail 6 times here during the path of the comet along its orbit. You see that the tail actually increases its length when it's moving close to the sun, and also the inclination with respect to the orbit, I mean the angle with respect to the tangent, the radial direction seems to increase. We tried to do some more thorough analysis. For example, you see here, this is the table with the reference time when the comet passes through the orbit, the location, the speed of the comet itself, and then we calculated this angle, theta r and phi t, that are simply the angle between the radial direction with respect to the sun, that is highlighted with this green arrow, and that tangential direction with respect to the motion of the comet, that is highlighted by this black arrow. So this angle are between, with respect to the radial direction, of 2 degrees up to 13. So when we move farther closer to the sun, this angle increases, while the angle with respect to the angular direction decreases. So the point is, the tail that we observe, it's a plasma tail or it's a dust tail. Usually, I mean, this is about me because I'm not able to distinguish the nature of the tail in the wildlife images of the coronagraphs. So we can disentangle them when both tails appear simultaneously in some observations. 2 minutes, almost the... So what we did is just to compare this deflection angle that we have measured here with a model for a plasma tail. Essentially what we did is to use the solar wind speed as a free parameter. Using the solar wind speed as a free parameter, calculate the relative velocity, and we get this angle alpha, that would be the theoretical deflection, that we can plot as a function of time. Here we have this data point we have measured, show the deflection with respect to the radial direction and with respect to the tangential direction. Actually, there is not a very good agreement or correlation. You see that some points follows in the lines that belong to a solar wind speed of 250 kilometers per second, other for lines that are a little bit with speed higher, and some are completely out. So probably this tail is not an ion tail, it could be essentially indeed a dust tail. In order to model the dust tail, what we did is to plot these Sindine curves for different values of beta. Beta here is not the plasma beta, but is the ratio between the radiation pressure forces and the gravitational forces. They can be explicit also in terms of this factor here, where C is a factor that contains the fundamental constants that appears in the radiation and the gravitational forces. Then we have this factor Q that is a scattering, just a coefficient that give an estimate of the scattering efficiency of dust, but can be approximated to 1. And then here the denominator we have the density of this dust times the size of this dust here. So what we did is for different value of beta to trace these Sindine curves with respect to the location where we sampled the tail at for different tails that we measured along the orbit of the comet. These are very preliminary results. Indeed, here we have a problem. We should model very well the injection time, etc. But it seems that value with beta equal to 0.5 are fit quite good, very good in a good way the location of the tail that we observe with the coronagraphs. Another point is that, as I said, with the solar orbiter Metis, we have also observation from the UV channel in the neutral line of the neutral hydrogen in the Lyman alpha, and essentially from the properties of the tail that we observe in the UV. So this will be the comet observed in the field of view of Metis in the Lyman alpha. This bright spot is just a very big, just a star. And from the properties of the tail, essentially the exponential decay of the emission along the tail path the deflection with respect to the radial direction, also the opening angle that is highlighted here with these yellow arrows, we can infer the properties of the local medium. So essentially the coronal density that we estimate in terms of 1.2 or 0.2. Here I think I forgot some exponent, some power. It should be 10 to 4 particles per cubic centimeter. Then the solar wind speed is around 200, is almost 200 kilometers per second. Also we infer the temperature of protons that is 8,000 Kelvin. Okay, so these are my conclusions. Essentially here what we did is just to show the first observation of a increasing comet observed with solar orbit and Metis, in conjunction also with other space coronagraphs that allowed us to make geometric triangulations. And most importantly, we have a simultaneous observation of this increasing comet in the visible light and the ultraviolet light. Okay, there is more work to do, of course, and also some other studies are work in progress about also the comet Leonard that was observed last year in December. But this was not a increasing comet, but was an Helios comet that has a perihelion at 0.45 astronomical units. So thanks for your attention.
Okay. Thank you. So we just have one question from Bill, I guess, and that's it. I'm sorry.
Very interesting, Giuseppe.
Thanks.
One thing I was wondering, I didn't follow exactly how you analyzed the tail. Mainly you were looking at the angles and the two models, right? In the DeForest paper, 2015,
yes.
We were able somehow, because Craig is really good, able to follow individual features in the tail.
Yeah, but
you can you not do that in these cases?
In this case, no. I think. I mean, in the work from Craig, I think they find some feature coherent that move away from the
bright points. Yeah.
Yes.
But this didn't seem to have.
In this case, no. It's a very tiny event.
What do you need, a bigger comet or something?
If you have a bigger comet, I think yes.
Maybe throwing off more stuff. Oh, okay. Yeah. Interesting. Really good.
Okay,
yeah.
So since we're only running late of 3 minutes...
but before I leave, I would like to make some advertisement.
Yeah, okay.
So there is a special issue on Frontiers about observation of the corona in inner heliosphere with Parker Solar Probe and Solar Orbiter. So those that are interested to submit some work about observation with remote sensing, they are invited to do. Thank you. Yes.
You have already ruled out the plasma tail, but
yes, but
you haven't mentioned the role of the magnetic field. Is there a way to
in the dust tail on the plasma tail?
Plasma tail. So is not the pickup depending on the magnetic field orientation in a way that this can?
But if it depends on the magnetic field orientation, also the solar wind should, I imagine. Here we are at altitude of 10 solar radii, yeah. So I don't know. I think the magnetic field is quite complex. It's not fully radial, of course.
Okay.
But the points that I have selected, the three-dimensional points, are in the plane of view and in the plane of the orbit of the comet. So they are not out. So if, well, I don't know, but if there is some action from the magnetic field, I imagine that this point could be a little bit offset from the plane of the orbit.
Okay, yeah. So let's thank the speaker once again more and welcome the next speaker. So the next speaker is going to be Trevor Bowen, who's going to talk about in situ observation of quasi-linear cyclotron resonant heating.
Great.
It's going to work. Just push.
Great. So real quick before I get to the actual science, I just wanted to plug SolarWind 16. This will be next summer in Monterey, California, at the historical site. I think SolarWind and SolarWind number 2 and 3. We actually have a website up for this. If you're looking for more details about it, we'd love to have you all come. This was postponed from 2020, I think. So for the science. Today I'm going to talk a little bit about some observations of sort of direct measurements of cyclotron resonant heating that we've been making with Solar Probe. I'm talking about a work that came out in PRL a couple of weeks ago. We actually got some press out of this, which is fun when you actually get some kinetic plasma physics out there. And also some more recent work that is soon to be submitted about sort of the signatures of cyclotron resonant heating on turbulent cascade. So sort of where I want to start with this is just talking about, the general concept that it's these kinetic scale processes and the kinetic distribution functions that give rise to the macro scale structure of the solar wind. These things that we talk about like density, velocity, and temperature are truly just moments of a distribution function. And these macroscopic thermodynamic properties represent the average properties of these distribution functions. So in the solar wind, we're very familiar with the idea that we have non-Maxwellian distributions and distributions that are out of local thermal equilibrium. So when you have heating in the solar wind, we don't have a type of thermal heating where energy is going in and rescaling everything as a nice Maxwellian or Gaussian. We actually have these very strange distribution functions that are fairly complex. And what's nice is that the complexity in these can actually tell us something about the signatures or the processes that might be heating them through looking sort of the signatures in these. I'm going to particularly focus on cyclotron resonant heating. So where you have some resonance between counter-propagating waves and particles through sort of just gyro matching of the wave phase speed or the wave frequency to the actual cyclotron resonant motion. So the damping of waves occurs through or leads to plasma heating through resonant absorption of the particles from the waves, and conversely, the emission of waves can occur through instabilities. So we know that ion cyclotron resonance is known to occur principally between counter-propagating waves and ions. So if you have outward propagating waves in the solar wind, they're going to be heating the tail or the back end of the distribution. So this is particularly a non-thermal heating process because you're heating particular parts of phase space where you have particles that can actually resonate with the present wave populations. And so it's nice because you can go and look in those parts of phase space and see if there's actually heating. So part one of this talk is sort of the signatures and the ion VDFs of cyclotron heating. So we're using sort of the framework of quasi-linear diffusion. This is Kendall and Engelman, 1966. And you can kind of work out the general average evolution of a distribution function in the presence of resonant interaction. So here's your integrated Vlasov equation, and this is sort of a function, sort of the spectrum of waves that you have, as well as this quasi-linear diffusion operator that depends on the dispersion relation for the ion cyclotron waves. The easiest way to sort of understand this in sort of 2 seconds is you can say, well, here's this operator in an equilibrium position. This has to be 0. df/dt is 0, so you're stable. And what that actually ensures by is this g of f is equal to 0. And this makes some of these nice contours in the VDF that you can kind of go and look for. In principle, if you have a pitch angle gradient that is negative, meaning that the distribution function is sort of sharper than these contours, the distribution function is stable to the waves and will actually absorb them. If you are exactly, pitch angle gradient flat, the distribution function is flat on these contours, you're in equilibrium, there's sort of no net interaction between the particle distribution and the waves. And if you have something that's, much, fatter than this, you'll end up with cyclotron instability or growth of cyclotron waves. So if we can go and measure the distribution functions and measure a spectrum of waves, we can actually get an estimate of a heating rate. Sure.
Because the algebra in quasi-linear theory gets confusing very quickly.
Yeah.
Just to be clear, are you talking only about standard cyclotron resonance
with protons?
Parallel
Yeah. We're just looking at, we'll talk about this in a second, but we're just going to use a cold plasma, ion cyclotron wave, parallel propagating.
There's no betatron resonance.
No, not there for now. Yep, so you have parallel propagating cyclotron waves We're going to find a spectrum of those. We're going to put those into measure distribution function, and we're going to try to calculate H from that. And so there's no oblique cyclotron resonance, we're just using the...
So if the turbulence were purely two-dimensional, there wouldn't be any resonance, right?
I'm not sure exactly. Sure, yeah. Right. Right, so this is, but what I'm looking at specifically is the circular polarized waves that we see. And I'll talk about this in a second. Sorry, I'm skipping through these. So essentially what I'm, in order to get a heating rate, you evaluate sort of this, V squared across the time derivative of the distribution function. And you can actually then just go and sort of start plugging in things. So if you can measure a spectrum of ion cyclotron waves, just K parallel, gradients of F of V, and then sort of assuming some cold plasma dispersion for parallel propagating waves. You have the cyclotron resonance condition, and you can just start trying to get a number for H out of there. So the hard part of actually doing this in the solar wind with electrostatic analyzers is that you're measuring the distribution function on a bunch of discretized bins. You don't actually have continuous functions to get, this G of F, which is essentially derivatives of F with respect to V. So you at some given time in the sort of V parallel, V perp plane, with all these individual points, and you have some sort of prediction of diffusion contours. And so the question is, how do you actually, do analytical integrals on this sort of bin? So we've looked at two ways of doing this. One is sort of the traditional way of doing a sort of two bi-Maxwellian fit. So you have drifting bi-Maxwellians to capture the Gore and beam populations. And we've also implemented a sort of Hermite decomposition using a linearly square fit of a bunch of orthogonal Hermite functions to try to capture more of the non-thermal behavior you see in the distribution function. So we can talk about this a bit more, but I just want to say, sort of put it out there that we're sort of using two different methods to try to capture this F of V, because it is something that's quite hard to do to get analytical estimates of the gradients. So using these types of fits, we can use that to figure out what we think the distribution function looks like, and then we can go and figure out what are the observed helicity signatures in the solar wind. And so this is a common way that people have historically used to figure out what the circular polarized fraction of the wind, or solar wind is. So you can go and take a wavelet spectrum, find all the circular polarized intervals, filter out those intervals where you just have circular power. You see that these are ion scales. You end up with some stuff that's left-handed circularly polarized, some that's right-handed circularly polarized. We did some work a couple years ago that showed that the intrinsic polarization is sort of statistically agreement with the spacecraft polarization, so that you can sort of just take all the left-handed stuff and sort of assume that that is predominantly an ion cyclotron wave. And so we're going back to this equation. What that gives you is something to put in here for your spectrum of cyclotron waves, I of k. You have these Hermite functions to put in for G of F of V. You have a dispersion relation from the cold plasma, and you can just put that in there and get H, which is just a heating rate. And so if you look at this value of H as sort of, a function of the sort of parallel resonant velocity, what we find is that the waves are actually pretty stable, and they're not actually being driven by any instability in the plasma, but they're actually being absorbed by the plasma, and then that means that they should be heating the sort of distribution function that's there. So we're able to get, using the bi-Maxwellian, drifting bi-Maxwellian fits, we get some number, 3 times 10 to the minus 15 watts per meter cubed. So we get some heating rate from the Hermite polynomials that's sort of on order that, a little bit bigger. And if we go and look at the Palatano-Bouquet cascade law and try to get an estimate of the turbulent cascade rate, well, we find that this is actually, 10 to 20% of the turbulent cascade rate. And so what this says is that the heating that we can measure using the spectrum of ion cyclotron waves and the measured distribution functions seems to be consistent with the amount of energy that's somewhat in the turbulence. And this, I think is quite interesting, sort of suggests that there is active heating that we can measure. Any questions?
This is for the period which you identify as wave.
Yeah, so basically what we did is we just took like a whole 6-hour day or 6-hour interval of data, because doing these integrals is kind of hard or computationally intensive, and just took out an average sort of parallel cyclotron wave spectra, assumed sort of a unity filling function, that this is kind of just what the background cyclotron wave spectrum is, and put that into this, routine to get out an estimate for H.
There's sort of a gorilla in the room with regards to this comparison, is that I think most people, both observationalists and theorists, would agree that the Peloton K law applied to the solar wind is probably
Yeah.
perpendicular cascade.
Sure.
Whereas you need parallel cascade to resupply.
Right. So it's a question of how do you generate cyclotron waves out of a perpendicular cascade. Right. But no, but this is, so what this is saying is if you go and actually look at the analytic, if you don't assume the Brazil plot, you go and look at the distribution functions, they are not driving the waves, they're absorbing energy from the waves. This is, everything that the contours that you get from the Brazil plot are essentially derived from a bi-Maxwellian approximations to distribution function. So this is saying that if you go and look at the intervals where the waves are, they fall in a spot where they're stable and they're not being driven by temperature anisotropy. That's the point of this, is that this, if you look at the heating rate.
The instability is already formed, it's into by distribution function, and then it's already stable. That's the mechanism of instability, how it works.
Right, so.
It's very low probability to measure instability at the very beginning.
So what we're measuring is a uniformly, you're drawing energy into the distribution function from these waves. There is very rarely that where we ever see any level of instability. So you have these waves, they're measurable, they have a couple nanotesla amplitude, and they are present with a distribution function that is actively damping them. So that energy is going into the plasma from the waves. There's no evidence that we can see of the plasma generating these waves in this interval. And so the question is, there's a good question of where do these waves come from? I have a slide at the end, but if we can make it that far, but we can talk about this later. How am I on time? Oh, cool.
When you show the polarization, is it near the knee of the power spectrum, right?
Yeah, it is, right. So this is kind of the next.
Is that the same order of the total spectrum?
Yeah, so here's the total spectrum. So there's actually much more right-handed stuff in this interval, but something it's about 1% of the energy is in the cyclotron waves. In this sense, but this is also this gets into I'm just looking at the parallel power spectrum here. This is the perpendicular because this is integrated over everything. So there's some work to do with that, but I can show some more slides. I think are connecting more of the turbulence to these waves that kind of suggests that their presence actually does mediate the turbulent signatures. So this is from a different encounter. I was looking at encounter 6, and this is just a day of data, and I was just chopping up the power spectra of these into a whole bunch of individual spectral intervals, and you can sort of see you have the canonical inertial range, you have some transition range in a lot of them, and then you have some kinetic scaling down here. And then you can go and normalize this to some KDI, where you see that sort of the transition range sort of occurs over the ion kinetic scales, KDI of 1 and K rho I of 1 is this blue line. And then you can go and find some cyclotron waves. And then I will just roll through this in a couple of minutes, we can talk about this. But if you start sort of normalizing the spectral signatures to sort of the total drop that you see over the transition range and the kinetic range, it seems to totally correlate to the presence of these waves. And that when you have these waves, you sort of end up with the sort of net drop over these scales that's much larger than if you don't have the waves. And I'm going to blast through this quickly so we can do discussions. But you start looking at how the sort of drop and sort of the decrease in power over the kinetic scales correlates to these waves. You basically find that having significant energy drops of is basically correlated to having these waves be present, which is also kind of strangely related to the level of the cross helicity. And so I think there's some evidence in here that sort of the presence of these waves is sort of affecting the turbulent signatures of dissipation at the transition range and kinetic scales. And do one more plot real fast and we can talk about it. And if you start looking at the intermittency when you have the waves versus you don't have the waves, you find incredibly different signatures, basically suggesting that there's strong Gaussian signatures below the scales when you have waves, and essentially intermittent turbulence when you have no cyclotron waves present. So I think, essentially we can talk about this more, I'll be here all week. It seems like we have evidence that the cyclotron waves are actually heating the plasma, and then when you go and look at how they affect the turbulent cascade, you actually find that there's a strong ordering of turbulent dissipation that's associated with the presence of these waves. So that is where I'm at with this, and I'm happy to discuss.
Okay, cool. We'll start with Bill and then go with the others.
So I have lots of questions which I cannot fit into this.
Sure, yeah, I can't fit that into.
But that last comment that you made, it seemed to me, if I understood correctly, you're saying that there's less intermittency when you have the waves because it's more Gaussian. Now that seems physically consistent with to the idea of waves because usually they're incoherent. But we also know from a lot of other studies that most of the plasma heating occurs near coherent structures, which means you have to have the intermittency. So did I understand what you say correctly?
So what I'm looking at is the intermittency far down, far below, I'm in the kinetic range, away from the waves. So it's saying that there are fewer coherent structures at kinetic scales deep in the kinetic range when you have cyclotron waves.
But at the scale of the waves, how about there?
I think that's really hard to... So there's a couple issues with that. One is you have very steep spectra there, and structure functions are not very good at capturing steep spectra. So there's an issue with trying to figure those out. I think trying to estimate, what the actual intermittent properties of the waves are is not, that's not sort of the goal. The goal is to look at how, the turbulent scales are being affected when there's these waves versus not these waves. Because basically what it seems like is there's some energy going in at ion kinetic scales that's either generating these waves or somehow these waves are mediating it. And then if you look at the kinetic range dissipation, the signatures look very different when that process is happening.
So are you saying 10% of the heating is from cyclotron resonance?
I think so.
Let's pin you down.
I think the Palatano-Bouquet has some major uncertainties in it, and I think... Yeah, definitely. I mean, I think that's the fact that you can get the right order of magnitude and that they're sort of consistent, I think it's 10 to 40.
That's probably the upper limit, Bill. So I have a quick question about this Hermite decomposition.
Yeah.
You could just look at the period where you have this ICWs and see how this Hermite decomposition varies, right? So that's probably one good way to tell whether or not you have the heating by those.
Right, so here's the distribution function evaluated on these waves, right? And so, on these contours. And so the contours are for ion cyclotron equilibrium. So you basically see a signature of equilibrium in the flatness of these contours, right? Does that make sense? So what this plot is that this is essentially, we are looking at the Hermite decomposition. We're not looking at coefficients, we're just using it as an analytical way of fitting the distribution function. So this is, if you evaluate the heating rate for each one of these, spectra, you'll get some number, and it's essentially always unstable, or it's always stable and absorbing energy from the waves.
The fact that this Hermite decomposition is a lot wider than the Bimax fitting is because you have higher order of M, so you look at those decomposition, the higher order of M gives you this contribution.
So that's not actually the distribution function, that's the heating rate. So this is saying that so this doesn't actually mean that it's wider, it means that you have heating at higher thermal velocities, parallel velocities.
Which is coming from the dF, d mu of those different orders, different M's. That's the heating rate coming from Hermite decomposition, is that right?
Well, no, I mean, it's just coming from evaluating this integral. So basically the Hermite functions are able to capture more of the non-thermal structure at larger parallel velocities. But I think that the net heating rate, it's basically what this seems to be saying is that the net heating rate in the Hermite polynomials is essentially saying that you're dumping it in at 2 thermal velocities. Yeah.
Okay, I have a quick question. It seems to me that what you're talking about distorts a Maxwellian to have a broader wings and narrower central
Yeah, I mean, so the thing, well, that's not necessarily the distortion that we're making. What we're trying to do is have, so the Maxwellian is actually just bad. It does not.
Well, what I wanted to say is that this is the opposite distortion to what you would expect from stochastic heating, where you get a broader central maximum and narrower tails. And what I'm looking for is a nice story to write a proposal for off-limb spectroscopy to study line profiles.
Right.
Would I be right to say that go with the Maxwellian, if you get broader wings, it's ion cyclotron resonant. If you get broader central maximum, it's something else.
I mean, I think this is quite, I think it's harder to say because basically it's a convolution between, a spectrum and the derivatives.
Yeah, but I'm trying to dumb it down for a proposal review committee.
Sure.
To tell a nice story.
Yeah, I think it's hard, I don't know, I'd have to think about how to dumb it down.
About my saying that. Okay, I just wanted to see what you thought.
Yeah.
Okay, let's thank the speaker again, and
thank you, everybody.
Will move. We'll move now to the last speaker of the session before lunch break. Last speaker is Anita Linnea Elizabeth Werner, and she will talk about turbulence and wave activity in magnetic clouds as seen by solar orbiter. Stay tuned. Let's see if it works. It should work. Let's see. Now it's doing something. You can go.
Thank you.
15 minutes at 12 I will break.
Okay.
And take the people interrupt.
Okay, and this
It's just for the stream. Oh, yeah, you can use this. And push this for the laser point. Okay.
Okay. There. Yes. So, hello everyone. Please tell me if I need to bring the mic closer to my face because I tend to speak quite quietly. So, if you don't hear me, tell me. So my name is Elizabeth, and it's fine if you call me Anita because I have like 3 names. It's fine. I'm a postdoc at the Swedish Institute of Space Physics in Sweden, and my colleagues and I, shown here, among them Emilia, who is here, we're studying turbulence and wave activity inside magnetic clouds in the inner heliosphere with the use of solar orbiter data. And today I will tell you a little bit about our current effort to find Whistler waves inside magnetic clouds using an algorithm and high-frequency magnetic field data from the Search Coil Magnetometer on solar orbiter. And this is a work in progress, so any comments and suggestions are super appreciated. Let's see if I can change the slide. Yes. So some basics first. A CME, or a coronal mass ejection, is a large eruption from the sun, which drags huge amounts of hot plasma and magnetic field with it. And when it propagates into interplanetary space, it becomes an ICME and develop these regions shown in the sketch on the left, which have different characteristics when measured in situ, as shown on the right. So if it is fast enough, a shock forms in front of the ejector. And it is seen in situ as a jump in all plasma and field parameters, basically. The sheath, which comes after, consists of shocked solar wind plasma and is characterized by a fluctuating magnetic field, high speed, density, temperature, and plasma beta. While the ejecta, which is the last region in the in situ data shown here, is characterized by high magnetic field but smoothly varying magnetic field components, as can be seen by the magnetic cone and clock angles. So you have a rotation. You also have low density, low temperature, and low plasma beta because it is the magnetic pressure is dominating over the thermal pressure. So we're looking specifically at the magnetic cloud, so the flux rope. And we're looking, in this case, at Whistlers in these magnetic clouds. So ICMEs are partly responsible for the injection of free energy into the solar wind plasma, which can drive turbulence and instabilities, which can cause wave formation. Recent studies have mostly focused on turbulence and wave activity in the magnetic sheath of ICMEs because these are so turbulent. So it's a perfect growing ground for these kind of things. But both mirror mode waves and electromagnetic waves near the proton cyclotron frequency have been found in magnetic sheaths. Mirror modes have not been found in the magnetic clouds, but lower frequency waves have been found. Overall, it is found that wave observations inside MCs are less common than in the sheath and in the solar wind overall, at least at 1 AU. And it is of interest to study whether waves inside MCs are more common close to the sun. So Whistler waves in particular, there's not a lot of data or a lot of published works on their existence in magnetic clouds. Whistlers are characterized as field-aligned, narrow-band, right-handed circularly polarized waves, found at frequencies between approximately 0.1 to 1 times the electron gyre frequency. But there are also waves which are not as field-aligned, which are propagating obliquely to the magnetic field, or the background magnetic field. And there are also instances of left-handed circularly polarized waves, which fit the other characteristics, both of which are less common than the regular ones. So when it comes to the solar wind, they can be very common, or well, still sort of. So early work have shown that they can be found in about 10% of the analyzed spectra from the solar wind when you look at cluster data. And that their occurrence could be linked to a larger electron heat flux than in the usual solar wind. Because electrons carry the major part of the heat flux in the solar wind, it is interesting, but it's not yet clear how they are generated under different solar wind conditions and how efficiently they affect or impact or interact with the superthermal electron population. There are also oblique whistlers, which we will not talk about more, are particularly efficient at diffusing these electrons, but they are less common than the field line variety. And we find that the field line variety is much more common in MCs than anything else. So we have developed an algorithm to find Whistler waves inside magnetic clouds, observed by solar orbiter at different distances. So we study snapshot waveforms of the fluctuating magnetic field from the search coil magnetometer, which has a sampling frequency of 256 Hertz and a duration of 8 seconds. So here you can see the polarization analysis of a few minutes of data. And these waves can be found by these blobs of positive ellipticity and low theta K, and enhanced fluctuations in the magnetic field. So we also use burst data from the fluxscape magnetometer to get the background magnetic field, or the direction of it, and to cross-check our wave events. So we first perform the polarization analysis on a larger interval, where we look at the degree of polarization, the ellipticity, and the relative angle between the wave and the background magnetic field. Then we use a sliding window of 4 seconds to identify candidate events which have a degree of polarization greater than 0.7, a good ellipticity or positive ellipticity, and which propagate within 20 degrees of the background magnetic field, so averaged over those 4 seconds. And we use 2 different frequency intervals between 0.1 and the whole electron gyro frequency. And if we get a hit in any of those, then it's a candidate. Currently, there are quite a large fraction of false positive detections with the current version of the algorithm. So I look at each candidate separately to identify the wave properties. And in the end, we find several events inside MCs observed by solar orbiter since mid-November 2021. And here we will talk about 2 or 3 of them in particular. So these 2 plots show 2 ICME events and 3 MC intervals that we will study more closely during this presentation. So the first 2 MCs in the first ICME event are associated with a complex, possibly interacting ICME structure, which is why we observe two, well, relatively easy to identify MC intervals and a very complex, large magnetic obstacle in between them. The orientation and the magnetic field strength of the two MCs indicate that they may be part of the same magnetic flux rope, but it's not very clear because of the level of perturbation in the middle. As such, the first MC is an example of a clean, relatively unperturbed MC, while the second MC is much more perturbed. And this ICME was encountered by solar orbiter rather close to the Earth at 0.8 AU or something like that, while the third MC in the second ICME event, highlighted to the right, was encountered closer to the Sun, near 0.4 AU. There are two potential MC intervals in the second ICME, but on the right, but we will look more closely at the second interval, which is highlighted because the magnetic field strength, that's the issue sort of with whistlers, if you want to identify them, with the search called magnetometer, because the magnetic field strength can't be too high. In that case, the electron gyro frequency is just too high to identify any whistlers. So we try to find, especially close to the Sun, ICMEs with low, relatively low magnetic field strength. Yes, and the properties of the middle section between the two smooth intervals in the plot on the right might be due to heliospheric boundary crossing or an SIR. But we will not talk more about that. It gives us, so this gives us a little bit of statistics to work with, enough so that we can start to compare how the properties of the whistlers and the background solar wind vary between different magnetic clouds with a different level of perturbation, and this is from Sun. So this analysis is not yet complete. We have more whistler events in more magnetic clouds to analyze and more data to look at. So this is just a taste, really. But what we can say so far is, firstly, for these three MCs, we find that the whistlers tend to occur in a rather narrow solar wind velocity range, between 400 and 500 kilometers per second. The range in temperature is much wider, which can be partly attributed to the higher level of uncertainty in the temperature estimate. But it's still low because it's magnetic clouds. The peak frequency is typically centered around 0.1 times the electron gyro frequency, as is also the case in the solar wind. There is also a second population of waves at slightly higher frequencies in this case, which might indicate there could be two different bands of whistler waves, but as it turns out, the high frequency waves are from a single MC in this sample. The duration ranges between 0.5 and 8 seconds, so the upper limit in this case is due to the time duration of the snapshots. Because most of these waves occur at relatively low frequencies, however, we can cross-check with burst data from the Fluxgate magnetometer to get a better upper estimate of the long-duration waves, because there are definitely longer duration examples. The bandwidth is typically rather narrow, between 0.1 and 0.2 times the electron gyro frequency, but there are cases where we have waves with wide bandwidth. Generally, the bandwidth seems to increase with heliocentric distance, which is not in agreement with previous solar orbiter observations of whistlers in solar wind, but this could be due to the small sample size in our case. We will find out. We find that the occurrence rate, not shown here, is 40 times higher in the perturbed MC compared to the first MC from the same ICME event. The occurrence rate is also higher close to the Sun compared to the first MC, but lower than the perturbed MC. Finally, we find that bandwidth is higher at large distances from Sun, as I already said. And although quite similar in terms of solar wind properties, if we look at the plasma properties and the peak frequency separated by different MCs, we find that the plasma still has slightly different properties, and this might significantly affect the wave properties. So clearly there is a fair bit of variation between different magnetic clouds, depending on whether they are more or less perturbed in particular. So we have a look at the power spectrum of the different MCs to try and understand, for instance, why Whistler seems to be so much more common in the perturbed MCs. So these three plots show the power spectral density as a function of frequency for the three MCs observed by the solar orbiter DC magnetometer, so keep that in mind. So it will not show the Whistler range, but it will show if we have lower frequency waves and that sort of thing, or if turbulence is fully developed. If we compare the different power spectra, we find two things. First of all, all of the spectra exhibit a two-slope feature, reminiscent of the solar wind, with an inertial and a dissipative range, with a spectral bump or break in between. And as has been previously shown for ICME sheaths as well, it seems that the ICME shock do not destroy the turbulence in solar wind. So this is true for the MC as well in our sample. The power spectra in the inertial range has a slope that is similar to Kolmogorow's power law in all three cases, but the second slope, which represents the dissipation range, have a wide array of values. Especially for the perturbed MC, which is in the middle, it's very low, so the slope is rather flat. And this might indicate that at small scales, the energy in the turbulent cascade is not fully dissipated, and there may be dispersive processes, such as wave-particle interaction, that generate additional cascade, which transfers energy to our high frequencies. A bit of PVI, and then I'll leave you with the summary. If we look at the partial variance of increments of the B field, we find that the PVI of B is lower in these MCs compared to your typical ICME sheath, maybe even the solar wind. But we do find that moderate PVI, above 4 or so, is not uncommon, but we do not have a lot of large field rotations, which is expected. It is noteworthy that the PVI is much, much lower in the perturbed MC. This indicates that we have a lot of wave events where the magnetic field is relatively smooth and free of discontinuities. So yes, I'll leave you with the summary to not waste your time.
Okay, let's thank the speaker. And now it's time for questions. Before the lunch break, it's time for questions.
So you developed, first of all, thank you for the talk.
Thanks.
You developed a technique to detect the whistlers as was done by Kretschmar, for instance?
Yeah, exactly.
So you detect all of them? So
yes.
Is it when you do that, you obtain comparable evolution as a function of distance as in this paper by Kretschmar?
That is one of the ideas, yes.
First question. Second question. Was not clear on your histograms the difference of whistlers inside the magnetic cloud and outside. Maybe you should overplot there all of them and then just put the one in magnetic clouds to really visually see the difference.
Yeah, absolutely. I mean, yes. So we have only looked at the magnetic cloud in this case, and clearly, since the properties differ so much between different events, it makes sense to look at the sheath of these events as well. So that is certainly something we can do. And
for instance, here I don't remember exactly what was the distribution.
Yes.
For instance, for the.
So on the top, it's the background solar wind properties.
Yeah.
For all of the whistlers in this case, for these three MCs, and then on the bottom, it's just the sort of to figure out the common properties and if there's I mean. It's such a small sample that it doesn't make a lot of sense to do this yet, but it's a work in progress. So
you can always put error bars there, which are something like
error bars is
square root of n divided by n, and then compare to the total one.
Yeah.
Okay. Thanks.
Thank you.
How did you determine the denominator of the PVI?
I'm not quite sure what you mean, but
Yeah. How large the interval was?
I mean, okay. So this is the whole MC, if it's understandable. So yes. Yes.
Other questions? What was the answer to that? The whole?
Yeah, the whole MC, so to speak.
Spectra that you showed.
Let's see.
Slide before.
Yes, I could.
So
Let's see.
One has a knee, steeper B. Number one is totally different. Number one.
Yeah. So these three slopes at the top, They show very similar values as we.
Well, I was speaking more in the dissipation range.
Yes.
Well, I mean the steeper part.
Yes. So this is the perturbed MC, and this has a much flatter slope than can really what we expect. So we expect the -4 or something like that.
Yeah, but I'm more interested in number 1 versus number 3.
Ah, I see. And I mean, yes, there is some difference here. For instance, here we don't have this very bump, really, more than a spectral break, and it might be due to low frequency waves.
But when you look at the PVI, it looked similar, no?
Yes.
For number 1 and
I'd
number
say
3.
so. Yes.
Yeah. So that's why I was just saying that these power spectra look different.
Mm. Thank you for pointing.
Okay, so if there are no further questions, we will have a lunch break now. And we will reconvene at 2:20. 2:20.
Un'altra volta,
But the streaming is not working.
C'è tutto, quindi. Dunque, forse è questa, però.
C'è il Thunderbolt con l'USB Type-C, se non c'è l'HDMI.
Sì, no, questa stavo pensando se si può usare quella.
on it is I do have a habit when I'm teaching my lab, because they have the meter sticks and the tubes. The 2 meter sticks make me feel it. I'm sure the students would love to hear me say, you shall not pass. Yeah. Yeah, that might not be a bad idea. Yeah, I should get them all for that.
Yeah, I hydrated with the last one. Just one? Ah, I see. Well, because of this. Sorry, I don't want to push it too. I have no more work to do this week. I'm done.
No,
I'm surprised you don't have
it's
one.
Florence, you have shopping, the museums to go to. It's not work. It should be in Florence.
Oh, because the windows are ventilation. No, it's, yeah, it's not as pretty. I think it's a French one. No, actually, it is that one. Yeah, here especially. That has to be the wall. That has to be the wall. I want to find someplace that doesn't, that's not this forest place. No, yeah. Check with say.
foncière de l'espace.
Oui.
Qu'est-ce que vous pouvez...
Moi, en fait, c'est surtout pour l'association en partie associative. En fait, l'association possède le titre ciel espace, mais la rédaction est indépendante. Enfin, l'association globalement, il y a une dizaine de salariés, dont 7 c'est des journalistes. En gros, grosso modo. Et puis il y a trois personnes qui travaillent pour la partie associative. On fait le rencontre du ciel et de l'espace, on fait la nuit des étoiles l'été, on se lance maintenant dans la science participative, on met en contact des astronomes professionnels et des astronomes amateurs qui ont des bons télescopes. On peut par exemple avec un petit télescope, tu sais, tu peux mesurer les occultations d'étoiles par donc la science participative, on a organisé récemment une campagne d'occultation d'étoiles par cailloux pour IPAD pour la mission Lucide de la NASA. En fait, voilà, on organise tout ça. Moi, je suis dans le conseil d'administration. Je participe aux réunions.
Est-ce que tu payes pour ça ou...
Ah non, c'est complètement bénévole.
Okay.
Ah non, je fais ça complètement bénévolement. Ça prend beaucoup de temps, mais je fais ça bénévolement. De toute façon, maintenant, en plus au CNRS, maintenant, la règle est que ta carrière peut évoluer en fonction de ce type d'activité.
Ah oh, ok.
Ça compte là. À Autriche, ça compte. CNRS. Bon, moi, je commence à être à un niveau où ma carrière ne peut pas beaucoup évoluer. Mais bon, c'est toujours intéressant. Ça m'intéresse. En plus, quand j'étais jeune, j'étais astronome amateur de l'âge de 12 ans, jusqu'à ma thèse, j'étais amateur, je faisais des observations, etc. Puis je donne plein de conférences. J'ai donné une conférence. Il y a eu beaucoup de questions, tout le monde était content. C'est ça? Paris-New York au 31 secondes.
I have no preference.
I saw the HDMI there.
I don't want to deprive you of your laptop.
Yeah, if you have it on
Je ne savais pas ça,
flash
je ne
drive
sais
or
pas ce
DVD.
résultat. Mais tu sais que
I
nous,
do
on
have
joue
one
sur
flash
l'orbiteur, avec nos poussières, à l'orbite de Vénus, on voit
Given the connection issue, maybe not.
une petite augmentation.
I mean, but are you
Voilà.
need it during my talk?
C'est le premier place.
Ah ouais, j'avais plein de questions. Les gens ils sont
You're supposed to say, oh, no, of course, I will be paying so careful attention to every word. Person who will be voting on whether or not I
qui
graduate.
m'a même remercié.
Well, it's sort of similar to that.
C'était passionnant.
If I didn't know what to say by then I would have, 10 minutes to later.
Ça, c'est bien.
Le gamin, ouais. Ah non, il est bien. En plus, il a oublié. En plus, je lui filais un t-shirt PW. Mais lui, il n'est pas con, hein.
Mais tu sais, ces gamins, ils ont des questions qui sont vraiment très profondes.
Ah oui.
Très profondes.
Ah bah oui. C'est des super questions. Ils ont du questionnement qui est très intéressant. Ah oui, toujours. Moi, je fais des trucs à l'école.
love UD.
pas mal de choses comme ça. Mais bon,
A few years ago, I transitioned to a
après, il y a enfin, voilà, c'est de...
black
J'ai pas mal de trucs sur...
a black bag.
Sur
What
l'orbitaire,
I realized
il y a
is,
encore dans
one
la
time I was
phase.
sitting at a conference, so it's
Il y a des choses qu'on va reprendre. Voilà, grosso modo,
yeah,
on est
it's
2 ans après. Enfin, 2 ans de retard, entre guillemets, dans la compréhension de l'instrument. Par rapport à ce qu'on
yeah,
c'est 2
PDF.
ans
It's
après.
not animated or anything.
Par rapport sur l'Europe.
Par rapport à Parker Solar, par rapport à Fields, tu vois, par rapport à Fields, on est 2 ans.
Mais les 2 ans, c'est un peu le lancement des deux. Il y a 1 an et demi.
Oui, 1 an et demi. Ouais.
1 an et demi.
Oh yeah, I'm third. You're in Europe.
Mais pour pas que Parker sur l'Europe, on a
Well,
beaucoup de chance que
yeah.
le spacecraft fonctionne. C'est almost a year. C'est vraiment... Sinon, on aura
Oh
beaucoup de
yeah,
problèmes.
we can't ignore them.
Non, mais il y a tellement de trucs, il y en a pour... Il y en a pour 10 ans, si on regarde les cours. Voilà, tu vois, par exemple, il y a des gens qui sortaient encore des résultats de Helios, tu vois. Les 2 missions ont excité les gens pour qu'ils regardent Helios. Il y avait encore des trucs intéressants dans les vidéos d'Helios. Donc c'est toujours ça.
So, j'ai une idée. Je pense qu'on doit le faire. Bon, moi j'ai...
Okay. It's okay. I understand English.
This idea came to me because of the table. I know ESA probably don't have a similar process.
No. Unfortunately, ESA is, really frankly speaking, the program is really in a bad shape, I think. C'est mal défini, c'est mal étudié. Ils veulent tuer Athéna. Ça va être le JWST, parce que le JWST a été pour la NASA, c'est-à-dire des multiplications par 10 du budget. Après, ça ne va pas être par 10, mais il va y avoir forcément une multiplication si on veut faire de la navigation correctement. Et si tu veux, l'ESA n'a pas les moyens de tuer le reste. Toutes les missions là qu'il va y avoir, c'est des discussions pour 2035, 2040, 2045, à mon avis. Ça n'a pas de sens alors qu'on a ces 2 gros mastodontes qui doivent pomper tout l'argent.
Hopefully that'll speed things up so you
Pas
can
assez
have a
d'argent
little more time.
pour la science et les arts.
I usually always do
Le budget de l'ESA, c'est en gros le budget de toutes les liophysiques.
like in
Facteur 5. Le budget de l'Equifox, c'est le budget de tous les arts pour faire toutes les missions de l'ESA, y compris toutes les grosses missions.
Mais en principe, l'Europe est thématique, c'est le plus riche que les États-Unis.
Oui, mais si tu veux, tu as toujours eu ce souci que l'Europe n'a jamais investi autant que l'ESA. Tu pourrais imaginer pourquoi
Lorsque tu vois une mission comme Parker sur l'Europe, tous les reviews et tout ça, c'est l'argent qui veut repasser ici. C'est énorme. Mais en quelque sorte, c'est une manière pour la NASA de l'argent dans le centre.
Toujours, sauf que l'autre problème, c'est que tu as quand même l'ESA et puis tu as quand même les agences nationales qui restent. Et un des problèmes, c'est qu'il n'y a pas chacun a ses...
Yes, okay, it's a picture, but at the same time, it verifies some formula, right?
ses actions, ses projets nationaux. Et après, il y a les actes, après, il y a trop d'acteurs.
For example, if I
Aux États-Unis, tu as la NASA, qui a tout l'argent, et qui le distribue. Tandis que là, l'argent, il y a plein d'entités qui ont l'argent. Et c'est forcément bien défini. Mais même globalement, c'est moins d'argent que c'est l'argent. Spatial, je sais pas, aux États-Unis, le militaire, ça doit être énorme. Un facteur 7. Après, on peut discuter de l'idée.
Let's go.
Je finis ça.
Thank you, Chevy. C'est très froid. It's good to have windows that you can open. But if you cannot open it's really...
At least he has a coat. I didn't bring a winter coat. I didn't think it was going to be
That's a winter coat.
Oh, that's not a winter coat.
No, it's not.
That's a raincoat.
Well, I mean, I bought this in Florence last year, so there are plenty of wonderful coats. And I told you last night my Dior story. My Dior story. I really wanted to buy the black cashmere double-breasted with the fur for $5,500.
Everybody does. I know about it.
No.
Just call
But okay, maybe I keep here indeed. So, how many minutes is once you protect the commodity before 3 minutes is fine. So 15 minutes of talk plus 5 minutes question.
And this is
yes, I guess you
No, you can use directly the USB-C.
Oh, I've never tried that.
Okay. And then we should move to
That's
should appear. Yes. Right.
I'll be up here in the heckler seats.
Okay. Yes, that's fine.
Oh, it's yours. We were wondering.
Just needed you open.
No, I could never do that.
I talk about ion instabilities.
Very good.
So, please take your seat. We are going to start the afternoon session. So, I think let's start. So take your seat, please. So, the first talk of the afternoon session is given by Daniel Verscharen. He will talk about electron-driven instabilities in the solar wind.
All right, thank you very much. Good afternoon, everyone. Thank you for coming back from this excellent lunch break. So I'm going to talk a bit about electron-driven instabilities. The title is quite general, and that's because I'm going to present in the first half of this talk a summary of a review article with the same title that has been published earlier this year. I was invited to submit this review article to a special issue in memory of Peter Gary, and I was asked to write about electron instabilities. And because at the same time we were an ISI team led by Anna Tenerani and Maria Elena Innocenti, we decided to have this review article as one of the main outputs from this ISI team. And in the second half of this presentation, I'm going to talk about some very recent work, and not finished yet, about an instability that is driven by this electron deficit that Chris mentioned this morning in the observations. So it's a new instability, and I'm going to show you how we are trying to understand that better. If you want to read up on these things that I'm going to summarize here, this is the title of this review article, and at the end I'm going to show you like all the different instabilities that we discuss in there, and so you get an idea if there's anything in there that you might find of interest. I will. Maybe just as a motivation at the beginning, we've heard about electrons already this morning. The electrons are actually, I would consider them a very important species in the solar wind. They've often been neglected just because they are so light, right? Almost 2,000 times lighter than a proton. However, there are more electrons than any other species in the solar wind, right? Because you have to create quasi-neutrality. And there's a lot of really interesting kinetic physics happening in the electron distribution function, which is also important for the evolution of the solar wind. And I think we're going to hear a bit more about this in the rest of the afternoon session today. On the left, there's just a general illustration to summarize these kinetic properties, or the main kinetic properties that we see, especially this structure consisting of these three different populations of electrons. Right? So we have a thermal core in blue. If you look at this in 2D space, V parallel, V perp space, you can illustrate it a little bit like this. Then you have the superthermal halo component, which is sometimes represented by a cover distribution as a way to capture that mathematically. And then, of course, we have this strahl population here, so a group of electrons that stream in the form of a beam faster through the rest of the distribution. And this already shows that we have these non-equilibrium properties in the distribution. So, for example, in this case, right, this beam is already a very clear example for that. We also see temperature anisotropies in the electrons. And of course, all these features can drive kinetic instabilities if they are strong enough, right? And that is kind of like the goal of this review article, was to discuss these different instabilities that can be driven by the electrons. And just to summarize this quickly in 2 points, so in this article, we develop like a semi-graphical framework, and I'm going to show you in a moment what I mean with that, based on the equations of quasi-linear theory. We've heard about this already in Trevor's talk, to describe these instabilities, and then, well, apply that like by going through many different types of instabilities, but I only pick 3 examples in this talk. Very busy slide, just for the quasi-linear theory aficionados here. So these are basically, this is a summary of these quasi-linear equations that describe the evolution of the distribution function f, or f0, the slow evolution of this background distribution function over time under resonant wave particle interactions. And those instabilities that we mostly focus on are those resonant instabilities. We also have a small section on the non-resonant instabilities. I'm not going to talk about that here. And the key point about this equation is you have these 2 G operators here, luckily the same symbols that Trevor used earlier, which are derivatives, right, in velocity space. Those are pitch angle gradients of the distribution function. And so we have a second order derivative there, which means this equation is basically just a more complex version of a diffusion equation. So we get diffusion in velocity space whenever the resonance condition in this delta function here is fulfilled, right? And then there are some further things here about the different right-handed, left-handed longitudinal components of the electric field fluctuations. I'm not going to talk about that too much here. And what happens then when you have this kind of resonance, we're trying to illustrate that always in this velocity space diagram. So if we have a wave that has a parallel phase speed here, this is basically omega over k parallel. And if you have electrons that sit, for example, here in velocity space, and if they fulfill the conditions for resonance with this wave, then they can start to diffuse, and they can start to diffuse, for example, in this way, as shown by this arrow here. And what you see is that an electron that would, for example, follow this arrow, and it's just an illustration in this case, that follows this arrow, this electron loses some kinetic energy, right? The distance from the center of the reference frame, which is just v squared, shown by the green circle, is getting smaller, right? So the v squared of this electron goes down, which means it loses energy. This energy has to go somewhere. It goes into these waves, so that's an example for an instability, right? So this is what I meant with this semi-graphical framework to describe that. So this is an example for a cyclotron resonance. If you have a Landau resonance, this affects particles that have V parallel that is equal to omega over k parallel. So they sit here, but they can also diffuse in this direction, or, I mean, in principle, they could also diffuse in the other direction, of course, right? But these are the ones that lose kinetic energy. These are the ones that can drive an instability. And this graphical framework illustrates conditions that you need in order for these instabilities to act. So let's look at some examples of these instabilities. Yes? Of course.
So since we're talking about the structure of quasi-linear theory, I have a couple of questions, and I'm serious. I really don't know the answer.
Yeah.
When you write this classic quasi-linear theory, you're assuming that the eigenmodes are Fourier modes.
Yes.
Frequencies that are associated with a given k.
Yes.
But if the solar winds, say, or the are organized as flux tubes, don't they have different eigenmodes? I mean, the eigenmodes of a free equilibrium flux tube could have, I mean, they're not Fourier modes. I mean, they're surface waves and things like that.
Absolutely.
Has anybody done quasi-linear theory based on that kind of basis?
Not as far as I know. I mean, this is basically the big question of kind of like the direction that Simon and I are going into now, like thinking about, well, how does all of this work? How do all these instabilities actually work in such a complex background, right? This is all idealized Peter Gary stuff, right? We have the homogeneous field, the homogeneous plasma with that non-equilibrium quantity, or uniform. Uniform is the right word, yeah. And yeah. Yeah.
Who look at like coronal, like
yes, yeah,
loops,
yeah.
and they do like a full set of eigenmodes,
right?
Labeled by something xn or whatever.
Yeah.
For those things, wouldn't that be a more appropriate basis?
Oh, definitely. No, definitely it would be for sure. But I mean, the advantage for the electrons is for electrons, because they are so light, everything they do happens on very small scales. And well, at some points it looks a bit smoother, right? But it's not a clearly answered question. But yeah, sure, yeah, absolutely. Yeah, everything about these instabilities in more complex backgrounds, I think, is a very important topic to look into. So we discuss in the review article, we then discuss 2 types of instabilities, those driven by temperature and isotropy, and I just pulled one out here. So this is basically the process that drives the classical Whistler anisotropy instability. So if you have a temperature anisotropy of this form, so in blue, that gives you again electron distribution function, and you have a temperature anisotropy that pulls it up in the perpendicular direction. So we have a T perp greater than T parallel in this case. Then the resonant particles can interact with this wave, and they can diffuse in this direction here. And you see already, right, these particles, when they diffuse, going from larger phase space density to smaller phase space density, these particles lose kinetic energy, and they give this energy to the waves. And we'll also see, right, it's nicely symmetric, so in this case, you would also expect that you drive the Whistler wave unstable going in both directions, right, going in the plus B direction and in the minus B direction. And so this is kind of like the graphical representation of the quasi-linear processes that happen in there, and you can even use that framework then to calculate instability thresholds, for example, and to predict the properties of the waves and of the evolution of the particles, at least during this quasi-linear phase. And it also kind of shows you what the nonlinear saturation, or the quasi-linear saturation, I should say, would look like in this case. And as I said in the article, we discuss bunch of instabilities driven by temperature anisotropy. And just to pick another type of instability, those driven by reflectional asymmetries in the distribution function. So this is, for example, an instability that has acquired quite a bit of attention recently. It's the instability of the oblique Whistler wave driven by the strahl of the electrons. And so you see the same thing here, right? These are particles that go into cyclotron resonance, strahl electrons that go into cyclotron resonance with this with a wave with this phase speed, and when they diffuse, they kind of like go in this direction around the phase speed, right? And they lose kinetic energy, give this energy to the wave, and that's a process that scatters strahl to higher pitch angles, and at the same time grows these Whistler waves. And also for that, we discuss a couple of different instabilities in the paper. Now, so this is the advertisement part about the review article. Now comes the new stuff about this deficit. And the first thing I would like to briefly motivate is, well, where does this deficit come from? Chris already mentioned this morning, it is related to this exospheric idea, and if we make this model super simple, and we just say we have a distribution of thermal electrons, and we have the interplanetary electric potential and nothing else, right? Then you can imagine that an electron that starts at the sun, out here, right, and has a positive velocity going away from the sun, if this particle is fast enough, it slows down in this potential, but it gets lost, right? It leaves the potential of the sun. If the electron is not fast enough close to the sun, then, well, it goes up the potential, and at some point, it turns around and falls back. And you can now imagine that, well, there is a velocity in the distribution function, in the outward part of the distribution function, that is just fast enough to escape, and if you were a little bit slower, you would be trapped. And those trapped particles are the ones that come back, and that then form this deficit in the distribution function. Of course, reality is a lot more complicated, right, because you have magnetic fields, you have other transport processes, but this is the basic mechanism that generates this deficit. And of course, well, you also have a magnetic field, right, so you get focusing and you get another reflection then by the mirror force when you come closer in. Okay, well, fine, right? I mean, all these things happen in addition, but we don't, for the reasoning of this instability, we don't need these other things. All we need is a process that kind of creates this deficit. And actually, these deficits can be observed. So this is an example from our PhD student, Joel Abraham, who has studied Parker Solar Probe distributions, and there are now some really nice visualizations of that from averaging over multiple distributions, but this is what that would look like in an individual measurement, right? So this is the anti-sun direction. See, the strahl is on this side. This is the strahl part, and you have the deficit on this. Yeah, so we can actually observe that in the distribution function. Yes, Simone?
I guess the same work was done by Laura also.
Yes, absolutely. You can. Absolutely.
Another comment about exospheric models.
Yeah.
Exospheric models are much older than the
Oh, no, sorry. If I didn't want to give an impression that this was the start of the exospheric theory. I only used these.
Last comment, there's collisions. So
yes.
vacuum can be solved also by collision.
That's right. Well, it depends on, but I mean, the thing is we see the deficit, right? So that means collisions are not strong enough to kill it off completely, right? So it is there. It's happening, right? And I said, well, there are all these other processes that are also happening, but all we need is something that creates this deficit. Because, well, I'll show something from Laura a little bit later for the measurements of this process. The thing that I wanted to really get to is, like, if you have such a deficit, right? And we go back to this semi-graphical framework of quasi-linear theory, we find very quickly that actually across this deficit, you can create exactly the right pitch angle gradient conditions for an instability to be driven by that. That's kind of like what I really wanted to get to. So not about the whole transport theory of the electrons. And the interesting thing is, so what that is electrons can diffuse across this deficit place here when they go in resonance with parallel propagating Whistler waves with this phase speed, and they would still lose kinetic energy, right? You see when an electron diffuses in this direction, its distance from the center of the reference frame decreases, and so these particles diffuse in this way. They fill up the deficit and at the same time drive these Whistler waves. And of course, well, if you have an idea about a new instability, you have to do the usual things, right? Check this with linear theory, check that with nonlinear theory, and that's exactly what we did. Linear theory, you can imagine if you want to check that with a classical bi-Maxwellian solver, you can't do that because bi-Maxwellian solvers can't handle this type of deficit. So what we did is we used our IAPS code, which can use any input distribution function to calculate the linear dispersion relation. We fed it with a smoothed cutoff, like a truncated electron distribution. The protons are just normal Maxwellian ones. And this, it's just here a Heaviside function. You have to be a little bit careful to ensure that you're still quasi-neutral and current-free, but we did that. And so we put that into ALPS, and indeed we find in the dispersion relation that the parallel Whistler waves are unstable, right? So this is K parallel wave number. In black, you have the frequency of the Whistler wave here. In red, you have the growth rate of the Whistler wave here. And this line marks exactly the right cyclotron resonance that we have inferred from this semi-graphical framework. And exactly at the point where the waves fulfill this resonance condition, you see the maximum growth rate of these Whistler waves. Great, so that means linear theory confirms what we found with our semi-graphical framework. And then Alfredo and Maria Elena offered their help with this, and we chose some PIC simulations. And instead of just picking initial particles from a Maxwellian, well, we picked them from a Maxwellian, but we said whenever the parallel speed of the particle is greater than the cutoff velocity, well, pick again, pick a new electron, right? And in this way, we created this truncated distribution function for the PIC simulations. And again, we have to make sure that we fulfill quasi-neutrality and the current balance, but we did that. And then you can start the PIC simulations. What you see is the same thing that we found in the in this graphical framework, right? So we fill up this deficit. The zero current condition pulls your distribution function back. We also see that parallel Whistler waves are created exactly at those frequencies where we would expect them, right? So these are the fluctuations in the magnetic field in the Whistler waves that propagate in this way. They propagate in the opposite direction of the deficit, also as expected from our graphical framework. And you can imagine that, we can also look at the spectral properties, and it confirms basically the same picture again. And then if I just have one more minute, I'll show you Laura's work, because that actually came before this whole theoretical explanation of these Whistler instabilities. She used EAS data from Solar Orbiter in 2021. It's in the first special issue of the Solar Orbiter first results. And she found this deficit in the electron distribution here in these very fast pitch angle measurements. And at that time, we already thought, like, okay, well, that's probably enough here to fulfill these diffusion contours that we need for instabilities. And indeed, she also found the Whistler waves together with these measurements in the RPW data, circularly polarized, nicely parallel propagating Whistler waves, fully consistent with the theory, the graphical framework, and the PIC simulations that we have run. And that brings me to the end. Here on this slide is the list of all the instabilities that we have discussed in the review article. So if you are interested in any of these, please have a look. And yeah, for the electron deficit Whistler instability, there are still some things that we have to iron out, agree on some parameters that we want to use that are most relevant for the solar wind. But we have kind of shown that it works, and now it's about really applying that to the actual parameters in the solar wind. Thank you.
Okay, we have already some questions, but if someone, Lorenzo.
Thank you, Daniel. Just a question. I noticed that not only there is a deficit, but also the distribution function is off-center. This is because the average...
That's right. You have to make sure. So we always calculate everything in the proton frame, just because once you choose a reference frame, you have to stick to it. And we always thought like a proton frame is the easiest one. And in the proton frame, if you want to get a zero current condition, and you cut off part of the distribution, you have to shift it over to make sure the bulk velocity is zero again. Yeah.
Is there any characteristic properties of the Whistlers generated by this instability which allowed you to characterize them and use as a diagnostic compared to other Whistlers?
Yes.
That we see?
So, I mean, I think the big thing about these is that they are unidirectional. They only go in the direction opposite of the deficit, while if they were driven by temperature and isotropies, they would go in both directions. And their frequency depends basically only on the velocity of the deficit. And the further you go away from the center of the distribution, the lower your amplitude gets because there are fewer electrons driving it. But in principle, you can drive them at any frequency, but you just have to make sure that the frequency matches the resonance condition with the deficit speed. And that's kind of like the link between them as a smoking gun, if you want. Well, I mean, I think what you need to do is actually bring that together, right? Bring together the electron measurement with the Whistler measurement. You can't just look at the Whistlers and say what they are. You have to match their phase speed. Yeah.
Very short.
Sorry if I missed something, but electron heat flux is non-symmetry of distribution function and deficit as well.
Yes.
So maybe it's just the same instability, just...
No, so people always call them heat flux instabilities, but of course they are not driven by the heat flux, right? They are they are resonant instabilities that are driven by the shape of the distribution. So whatever creates that, as you said, this asymmetric shape of the distribution is whatever drives the instability. So in this case, well, this is a form of a heat flux instability, but I would... Exactly, yeah.
Okay, if there are no other questions, so we thank Daniel. And we move to the second speaker. So Milan Maksimovic. Okay. So he will talk about the baseline solar wind. The USB-C should work. Okay. Should appear. Try in presentation mode. So we'll give you 15 minutes.
Do I use a microphone? I use a microphone. Okay. So thank you, Daniel, for actually you introduced a bit my talk. So the baseline solar wind, hopefully this will be soon submitted. What's the motivation? So you remember maybe a few years ago, I started to look at this, the data in this way, where here you have the Helios data. If you try to order the data by their speed, assuming that you have 5 classes of wind, and assuming that the order is the same as you go with radial distance. This is the closest radial distance. This is the one which is the close to 1 AU. You can then order the speeds in this way. There is no laser. Is there a laser? A stick. Where is the stick? Ah, voila, of course, this is a classical laser, which is very good, better. Okay, you can order this in families or populations or whatever. And what you can see here on this, as already here, is that you have a minimum solar wind speed, which is accelerated in this range between 0.3 and 1. So Jean-Baptiste Daqueau, who is doing his PhD thesis in Meudon and Toulouse, has added the Parker solar probe data to this statistical analysis, and he has also built some families, and clearly here you see even better this acceleration. So what is this very slow solar wind? Why and how is it accelerated? This is the question that we ask here. The second motivation, which is related, is a paper that in principle it's in preparation, it's not yet submitted by Stuart Bale. He has looked at the data here from various encounters, and this is the paper where he shows that here you have the bulk speed as a function of the time of the minimum approach, and all this is shifted by the longitude. It's a kind of, you remove the longitudinal effects. And what he has shown is that the solar wind speed is highly structured and organized in angular scales that you can kind of see here. I don't know if you have seen these talks or paper. There is also another paper by Naïs Farget about the fact that you have these cells which are corresponding to the supergranular convection cells. And in between those, you have these minimum speed periods, which are not actually connected directly to the current sheet. It doesn't seem to be the slow wind with the one connected to the current sheet, because it's not always close to the inversion of the magnetic field. You can see that on that speed. And if you put all the data together, you end up with the same figure as the one you have seen. And the question is, what is this minimum speed here? This baseline solar wind. So okay, I was kind of curious and motivated by this, and I looked at other data. So here are all the data I could find on the internet. So here you have Parker solar probe. This is Helios. In blue, all the Ulysses data, which are in the ecliptic plane. So I took the one when the mission left the Earth and went to 5 solar radii, and then I removed the polar passes. I just kept what is in low latitude. Then I took the Voyager data, the Voyager 1, Voyager 2. Here, Voyager 1 was close to the ecliptic, more than Voyager 2, actually. But anyway, what I did is that I took things which I like to do is to put things in boxes. So I take radial boxes here, and I took the 3% level, the 3% lowest level of the bulk speed here. It can be 3%, it can be 1%. It's not very important. And then you end up with the level of the 3% lowest speeds there. Okay? And this is the blue line. And this is what I defined the baseline solar wind. So here, there is already the start of the answer. This thing which is accelerating here, that we saw in the data from Parker solar probe and Helios, is still continuing to be accelerated. And then it is reaching a minimum level at large distances. So I played with this data. So here are the data. Here is the temperature for all these missions. So here I have concatenated the data from, again, Parker solar probe, Helios, up to Voyager. And what we clearly can see is that in the proton, there is no electron data on Voyager, not to my knowledge. For the proton data, we can see that after something like 1,000, 2,000, the temperature is kind of not varying as a power law. There is a kind of different physics, possibly an interaction with the neutrals coming from the interstellar medium. Possibly because here you have a lot of data which are out of ecliptic stream-stream interactions with the fast wind. The Boshock crossing is a bit further, still a bit further, I think. So there is a different physics. So this is why you see in another plot, I removed that. Here is the thermal speed which comes from this proton speed. And this is the form that I used to fit, and the black is the fit. Okay? So how to explain this minimum wind? So I go back to a category. Sorry? No, but we can try. Yes, yes. Actually, it doesn't work. Yeah, no. The isothermal. We spent a lot. Actually, we spent a lot of time with Stuart on his plot to try to make it fit. So you can fit with a logarithmic form for an isothermal. When you take a temperature which is a magic temperature of 1.7, I don't know what, and you have to divide by 2, and then it fits nicely. But it's not Parker-like. It's not Parker isothermal. In any case, it's not isothermal as you have seen the temperature. Yes?
If you have any kind of average flow and you add fluctuations to it, fluctuations are going to add to it in some places and subtract other places. Why would you consider the minimum to be of great significance? Isn't the median or the mean or something, isn't it more relevant?
Maybe, but here, I mean, what I want to see is, yeah, of course, but the mean of what? Of all the population or just the median of the lowest 3%? Okay, I mean, you can do the whole populations, but here we are focused on the really minimum solar wind, the baseline solar wind. I mean, this is a choice.
Baseline solar wind makes it sound like that's the starting point and everything else is added to it. Okay, but if you have a mean flow, I mean, measure the wind outside this building, right? It's a mean flow, and there's some places where any...
Okay, maybe the denomination baseline is not the best one. Maybe not, but I don't know. I mean, anyway, we decided to do that like that, but to look at really the slowest one, and clearly the other. Yeah. No, but then at some point you are reaching here, it increases, but you are reaching a saturation. If you see here, there is a saturation, which is this. I mean, this is a way of analyzing the data, and we have a way of modeling them. Okay. Yeah.
But you should see this also in the average, I guess.
The average of what?
You have the baseline increasing, the mean will increase as well.
Okay, but we have modeled. Okay, I mean we can spend. I will probably exceed my 20 minutes if you are asking so many questions. But here is the sample. So the sample is here, and the sample is here. So here you can do whatever you want with the data. The data are here. So what we can do is, okay, remove the colors. You have the data. You can look at the average of that. And then clearly, I mean, clearly here you can also look at the maxima if you want. I'm not sure that it is the same physics which explains here. My statement is that the physics which explains this minimum solar wind is kind of simple. It's a wind which can be explained by an exospheric kind approach and even a fluid one, as I will show. But here, what's happening here? Here you may have stream-stream interaction regions. You may have a mixture between a wind which is coming from coronal holes, which is coming from who knows where. No, here you have large fluctuations here. So I will never finish if right.
After a while, in the black regime, you can just say that, okay, the mean envelope is about 400 kilometers.
Okay, okay. You can make the assumption whatever is the, I mean, that there is just one source of the solar wind, which we know is not true. And then you can treat the solar wind as you see it as one single component. This is already, I do not think that you can do that. Because we know that there is a wind coming from the coronal holes which is fast. We know that there is possibly also some wind which is, you see the blobs which are above this, the blobs from Chile. If you look at the data, they are above this minimum baseline solar wind. And they propagate with the faster solar wind. Here the question is, you have this data sample, okay? I see that there are points over there. I can, if you want, I mean, that will be my next study. I can try to look and we can try to model the maximum. But I'm here for, I decide to focus just on the minimum that I call the baseline solar wind. I can do that. I'm allowed. Okay, I can do it. You allow me to do it. Great. Of course. Okay, let's see if we do that. So here is the exospheric approach, which is the historical one with all the developments. I will not go into too many details for that. But just to remind you that in the exospheric approach, if you plot the total potential for the protons, which is the electric field plus the gravity, you end up with these curves, where you have a maximum. The maximum is just before, but very close to the sonic point. Okay? But there are different values of the potential in this model because you have different curves of electric field. And this is due to the fact that here we have a model with kappa function, which is the one which can explain the fast wind. But you have always a maximum. So what's happening if you have a maximum and if you use this approach? So this is to explain you very quickly the cutoff. I mean, it was already presented and observed by Chris and by Daniel. But here, very rapidly, if you have the electron distribution function at a given distance, and I remind, I mean, there is a paper here which I wrote some time ago, already speaking about the deficit. Then you go and you define the escape speed for the electrons. Okay, and the escape speed for the electrons. This is another way to see the cutoff with respect to what Daniel just showed. The escape speed for the electrons is related to the electric field, and defining here the escape speed or the cutoff. So this is the cutoff for the electrons in the anti-sunward direction. This cutoff is directly a measurement of the electric field. So it is because we start to observe this with Parker that it's interesting because we can have an idea of the electric field. Of course, as you said, there are plenty of things, Coulomb collisions, that we should put there. We did that already with Laura and with Simone. Of course, instabilities and so on. So here is the deficit observed by PSP and solar orbiter, and even with Helios. At the beginning of Laura's thesis, we looked at Helios, and actually there are some deficits in the Helios data that we should have probably published that before. But anyway, this is an example from Jasper. So here you can see this is the anti-sunward direction. This is the sunward direction. So these are the Strahl electrons. This is going away from the sun, going to the sun. And if you see here this fitting by a Maxwellian, you clearly see the deficit here. You start to see a deficit. Of course, it's not a deficit which is sharp, because for sure collisions and Whistler waves or other waves or whatever instabilities are kind of making it shallow. But it's not a sharp transition, but you see the deficit here. A way to do that, you can plot the data divided by the core fit. It is 1 here, and clearly at the deficit there is a drop, and you can define it statistically this way. So it was done by Laura in this paper, which is the 21 paper, with an estimate of so this is the electric field compared to various models, including simulations. And this is the bulk speed which would come from the deficit. and this is the observation. So basically what we see is that, and these are the average, but not the minimum. These are the average here. And here are the minimum. And you already see here that the minima are kind of well represented by the electric field. So now,
2 minutes.
Going back to the protons, sorry?
2 minutes.
2 minutes. I'll try to be quick. For the protons, and by the way, there should be a deficit on the protons. So we should think about that. There should be clearly a deficit with the protons. If there is one for the electrons, of course, there is no, because there are instabilities and something is happening so that we see less deficit. I tried to look at the data from Parker Solar Probe, going very close. Okay, we know that the distributions, they are kind of a Maxwellian plus a tail. So if you take the overall distribution, maybe there is a kind of, you can model that with the deficit, but it's, okay, I agree with you, Lorenzo. But anyway, the deficit is such that the distribution should be here at this point of the maximum here of the total energy. And actually, as you go away, here is what should be the distribution functions for the electrons from the protons. So this is described in the paper, in the 2001 paper that I wrote. And when you are very far, the distribution function should be a half Maxwellian, which is pushed by the electric field, and which is, for which you can define very easily the bulk speed, sorry. It's obtained here, and here is the value of the average bulk speed that you get here as a function of this minimum speed, plus you have to add this contribution, which is the flux here, at the maximum of potential energy. And the minimum speed here, which is this value here, is simply obtained by that. So you have, this is a very crude exospheric model in which the bulk speed at a given distance from the sun is related to the electric field here here the electric field at the same distance, okay? And you have here to define the maximum of the electric field at Air max. So what I did here, I took the model, here only restricted to the distances closer than 2000 solar radii. So here is the model of the fitting. So this is the terminal speed of this baseline solar wind. Here I define the Air max arbitrarily to be here at the crossing of the speed. So this is where this is the sonic point. So I define my Air max there, and I impose the value of the potential there by just having, you can do the analytics, you can just get that from this value here. And then you end up with an electric field that I will show in the next slide. Just to say that if I restrict here the data to the same range, these are the protons, the electrons, these are observations, and these are fitting with power laws that I will use soon. So here is the electric field which corresponds exactly. So what I do here, I take the bulk speed and I look at what should be the electric field in order to have this bulk speed given this formula, okay? So here is the electric field. Now if I compare with the observations, it's here. So the green is the deficit from the Alekas paper for the slowest of the wind. If you look at the paper, there are several winds there, and there is the minimum wind. There is a kind of baseline. So to a factor of 2, it is kind of not very far. And the potential which comes from the electron here, sorry, this should be in red because the electrons are here. This should be in red. The electron gradient is giving you an electric potential. If you take this electric potential, you end up with this blue curve, okay? So now this is the curve which summarizes the modelization. These are the observations. The modelization with this speed which is imposed gives you this electric field, which is not exactly the one which is observed or inferred from the gradient of pressure. But if you do that, if you put the gradient of pressure, which is very close to this is interesting, very close to the Alekas electric field, you end up with the blue curve here, which is kind of fitting here at the beginning, but it's providing a lower here terminal speed actually. And the other thing is that if you compare that with a fluid model, so this is a fluid model coming from the paper by Jean-Baptiste, which just has been accepted, where you assume the solar wind to be isothermal at the beginning and then adiabatic after a given distance. So these are the proton model, electron model. So you just do Parker, nothing else. You impose these temperature gradients, and you end up with the pink curve, which actually fits very well, and this is normal because we know that the exospheric solution and the Parker solution are very similar. So it fits very well here. The blue and the pink coincide very nicely. It's this one. This one, sorry. You take this gradient and you compute this. No, it's no. It's here. So you take the gradient of that with the density. Sorry? No. Yes, of course. Electrons are red and protons are blue. This is the electrons, this is the protons. The temperatures, it's exactly for the same solar wind, the minimum one. I take the 3% level, I take the median value of the bulk speed of the 3% in each of the box, and then I take the corresponding proton and electron temperature, the one which are observed by the instruments. Yes, we know that in the very slow solar wind, the electrons are much hotter. The electrons are much hotter than the protons, and the slow solar wind is thermally driven by the electrons. This is well known. I put my conclusions, and then you can ask the question. Yeah, we should look at that. That's the next thing to we should look at that. Exactly. Because as Olga said, and as Olga asked and Daniel answered, the deficit, obviously the deficit is the heat flux. And clearly there is a link in all these models between in the fluid models and exospheric models, there is a link between the heat flux and the electric field. Yeah, because you have, So this is the conclusion. Anyway, there is a minimum solar wind. I mean, you cannot find, okay, statistically you will find accidents, but you will not find at a given distance a wind speed which is lower than the one that I give here, which is the baseline one, okay? We can define it this way. This baseline wind is continuously accelerated up to 4 to 8 solar astronomical units. It reaches a terminal speed, and it can be modeled by both fluid approach or actually exospheric approach, which are very, very the same. Just to make a comment, that is that for this wind, the deficit we observe and the electric field we can infer from the data, they are compatible. Clearly, right now, the deficit we get in the fast winds with the Parker Solar Probe data, they do not provide an electric field which is enough to accelerate the fast solar wind. This is for sure. There is a mismatch there. And if we like the exospheric approach, and I think in any case the deficit is something which is observed, and if it is the right interpretation of the electric field being coming from the deficit or imposing the deficit, that we should still explain the fast wind.
Okay, I was here to stop at the point.
I will stop now, yeah. Okay, there is probably some semantics there in the baseline. I shouldn't name the paper the baseline solar wind. I will still do it maybe, but okay, it's not the baseline. It's the minimum speed. I don't know if you want to call the minimum speed wind as a function of the radial distance. Let's call it this way, but it's longer than baseline. Okay, if you want. It's the slowest of the slow wind. It's the slowest of the slow wind.
Okay, Lorenzo has a question.
So you're saying you can produce this slowest ever solar wind using either exosphere or other winds that consist. But it seems to work up to like 180 or so.
I agree.
Beyond 180 you went to 80.
There is still something missing. I agree. There is still a little bit of, there is something like, you see, it's not a lot, it's maybe 50 kilometers per second. So we are missing 50 kilometers per second.
No, but then the question is, so is it something that you could provide with some more electric field, or is it reasonable and it's definitely about stream-to-stream interaction and other things?
I would say maybe it's baseline until here. I mean, an explanation could be that it's kind of baseline until here. And then after, I think you already start to have some stream-stream interaction, which is making the thing that the baseline is kind of perturbed. Okay, sorry to be long.
Yes, because I would like to give you the same opportunity to everyone.
Sorry? It's not your fault.
Okay, let's thank Milan. Now, the next talk is given by Bennett Maruka about radial trends in plasma parameters across the heliosphere.
Okay. I'll try. All right, thank you so much. So I'm actually going to be building on a lot of what Milan was just talking about, so thank you so much for the introduction. Merci beaucoup. Wait, where did my pointer? All right, so radial trends, I'm going to be talking about radial trends. So as we've seen, these are just plasma parameters as functions of distance r from the sun. And it's worth noting that this is an inherently reductive way to look at the solar wind, which is in fact replete with multi-scale fluctuations in space and time. And so this involves a lot of long-term averaging. Nevertheless, these radial trends are really important for understanding the theory of the solar wind all the way back to the very beginning. This is figure 1 from Parker's 1958 paper. Is showing, in fact, a radial trend in speed. So, since that time, we've collected quite a bit of in situ observations. This is a slightly out-of-date figure that I put together for the Vachar et al. Review paper, showing past, present, and future missions. We need to update Solar Orbiter to the magenta and extend the magenta bar in PSP. Also, Voyager and New Horizons are out a little bit farther, but the point is we have quite a bit of coverage, over 60 years worth of data now, and over 3 orders of magnitude in distance, over which we have the particle measurements and fields. So I'll be talking to you today about what we're calling the Trans-Heliospheric Survey, which is really an attempt to put together as much of this in situ data as we can and use it to better understand the heliosphere's large-scale dynamic structure. So we wanted to utilize exclusively publicly available data sets from as many spacecraft as possible and focus on the most fundamental parameters. For example, we were looking at the scalar temperature, but not the anisotropy, the temperature anisotropy. We also wanted to keep our fits and interpretations as simple and minimalistic as possible, not favoring any particular theoretical model, to make it publicly available to the widest possible audience, releasing our radial trends, both the data and the fits thereof for community use broadly. So here are our source data. We ended up using data from 12 different spacecraft listed here. The publicly available data sets mostly coming from CEDAWeb. We needed to go to OmniWeb for the Mariner data. So a huge shout out to the spacecraft teams, the instrument teams, and the folks behind CEDAWeb, OmniWeb, and CohoWeb. Most of these data sets were already averaged to a 1-hour cadence, but for all the others, we averaged them down to the 1-hour cadence. So we had uniform sampling. Everything was on 1-hour intervals. Like Milan, we excluded Ulysses data after the Jovian encounter. We also had a cutoff of 100 AU because at that point you're well beyond the termination shock and it's just a different plasma at that point. So here's what the data look like. We considered multiple parameters, but I'm going to spend a few slides focusing on magnetic field strength, so the magnitude of B, as an example. So here we have plotted the magnetic field strength as a function of distance from the sun. We have a different symbol for each of the 12 spacecraft. Notice that New Horizons is not represented since it didn't have a magnetometer. Up here we have the number of 1-hour intervals from each spacecraft, so you can see the coverage of, of the different spacecraft. And we divided up distance from 0.06 to 100 AU into 80 bins, logarithmically spaced. And you can see we have a general downward trend, which is exactly what you would expect. And it actually the data sets align pretty well, though you'll notice there's a notable disagreement between what was going on with what was observed with PSP and the Helios and Mariner missions. And at first we were thinking, is this a calibration issue, something going on? And the answer is really no, not really. The bigger issue is that this is relatively early PSP data, mostly from solar minimum. And in solar minimum, the magnetic field strength in the solar wind tends to be systematically lower. So we needed some way to correct for this. Otherwise, if we put all the data together, there'd be this sort of a kink here in the plot. So what we did is we turned... I'm sorry? Right, it wasn't just a minimum. It was a very minimal minimum. So to correct for this, what we did is we introduced this scaling technique where we scaled all the measurements to what was happening quasi-contemporaneously at 1 AU. And this is based on a technique used by Smith et al. Back in 2001 to look at Voyager measurements. So the way this works is you consider some parameter, K, the magnetic field strength, the density, whatever you like. And at some time, T0, when the spacecraft was a distance R0 away from the sun, you make a measurement of K, a value K0. And then consider, well, okay, when was that blob of plasma at 1 AU? When did that blob of plasma arrive at 1 AU? Assuming a steady radial outflow, it's just going to be T0, the time of your measurement, minus the difference in the distances from the sun divided by the speed of the solar wind. And so what we did then is we considered, okay, let's look at a 27-day average of the omni measurements of that parameter K, centered on that time T Earth, when the plasma was there, and then normalize or scale the measured value K0 by the 27-day average at Earth. So how does that magnetic field or density measured somewhere else in the heliosphere compare to what was happening quasi-contemporaneously at 1 AU? The quasi part I add just to take into account that we're accounting for the propagation time. And so when you do that, you're able to put the whole thing together. So here we're looking not at the magnetic field strength per se, but at the scaled magnetic field strength and all of the spacecraft together. And you'll notice it's pretty much smooth. The data are in purple, or I should say magenta, all the way through. There's no kink here. like there would have been if we had just put all the magnetic field data unscaled together. What we're looking at in purple is the dots indicate the median value in each bin. Again, this median scaled value across all spacecraft. And then we have vertical bars. They aren't error bars. They're actually indicating the distribution of data within each bin. So the thick bars are indicating the 25th to 75th percentile, the interquartile range. And then the thin bars are the 10th to 90th percentiles. Two of these points are outliers. These two out here have significant contamination from the termination shock, and so we excluded them from our fits, which are shown in the light blue. For the fits, we basically stuck to power laws because, again, we didn't want to impose any particular theoretical model on this to make this as broadly applicable as possible to the community. So the traditional power law would just be this. You have r to some power times some coefficient. But we found that that didn't fit the data particularly well in most cases. We had to add in a single break or, in some cases, a double break, which is what we had to do in the magnetic field case. So we have three different, in the doubly broken power law, we have three different power law indices. These initial coefficients here are just to ensure that the fit remains continuous. We used a nonlinear fitting routine to fit it so that not only were the indices free parameters of the fit, so were the locations of the breakpoints, the RAs and the RBs. And so we tried to fit with the least number of breakpoints possible that would still fit the data. So to go back to the magnetic field case, as I said, we had to use a doubly broken power law, so two breaks. The breaks are indicated by these vertical dashed lines. The fit itself is the solid curve here and all the way through here. And what we did is we are showing the extension of each power law segment with the dotted lines. So you can see, even though this is a relatively weak break here, it's a slight change in the index from negative 1.739 to negative 1.468. Based on these dotted lines, it really is a clear break there. It's not the biggest transition, but it's definitely doing a better job fitting the data. And so we felt that it was necessary to have both of those breaks there. And this is a really interesting case because you'll notice up here in the very inner heliosphere, you get a fall off going almost as 1 over r squared, not quite, but almost. And that's what you would expect if the magnetic field were radial, as predicted by Parker. It would be nearly radial there. But then as you go farther out, you would see a circumferential field where you would expect to fall off as 1 over r, which is very roughly what you're getting here. So it's a nice consistency check to see the Parker spiral baked into this result. Yes?
Just a comment, I see that your second break is close to something like 2, 3, 4, 4, 5 AU.
Yeah.
And this is corresponding actually to the when you plot at the proton temperature. This is where the, okay. Voilà.
See, and in fact, we only fit so this is the same thing, scaled proton temperature, and we didn't, like this, I had nothing to do about where the breakpoint was placed. That came out of the Levenbach-Marquardt algorithm. And it gave remarkably similar breakpoints for the magnetic field and the temperature. I mean, this shocked me because, remember, these are measured with completely different instruments, right? They have nothing to do with each other, and yet we're seeing this remarkably similar placement of a breakpoint. So this really does seem to be something going on in the solar wind, something about this point. What's going on there, I'm not sure.
It's interesting that it's slightly smaller than the so-called ionization cavity for the pickup ions, which is usually placed at around 7 or 8.
Yeah.
It's a little bit too close.
Right. I mean, it could be the effects of pickup ions. I mean, you're definitely not seeing anywhere adiabatic fall off. You know, the temperature's falling off fairly rapidly, but not quite adiabatically. And then it gets even less adiabatic out here in the outer heliosphere. There's certainly an increase in pickup ion heating out here, maybe. It is a little suspiciously close to Jupiter's orbit, which is right there. And yeah, and it's worth mentioning that Jupiter has a truly massive magnetosphere. I mean, its tail extends many AU, and every one of these outer heliospheric missions did a Jovian encounter. So is this some sort of a, are they seeing a lot of contamination from Jupiter?
Jupiter has really large amplitude upstream waves.
Yeah, so I'm hesitant to speculate on that, but it is something worth noting that it might not be a quote-unquote purely solar wind phenomenon going on here. Yeah. Right, unless it kind of... Yeah.
Right, but then the pickup ion is one thing that you talked about Jupiter's effect, which is something else. So why would that give you the same power level?
Yeah.
How long is the tail?
Yes, so you can find itself with the tail of Jupiter. So
Yeah, it's...
possible that it...
Yeah, it goes well out. It goes to at least Saturn's orbit. It's big. So again, I don't have a clear answer on this, but it's worth noting that it's there, and I think there's some interesting work that could be done here.
And in fact, there is sort of a secondary feature just outside of the 5. The temperatures go back up, right?
Yeah. This is Jupiter, this is Saturn. Yeah, this could be... Yeah.
But you're still assuming that Voyager stayed in the magnetosphere for a long time. Like, I don't know, I mean, I doubt that's even possible.
I think that this is a statistical view. I mean, of course, Jupiter was around the...
At some point, but not forever.
Yeah, I don't know what the chi-squares would be, but if you kept the, right after your vertical dashed line, you kept the next 3 points with the left-hand group, it wouldn't decrease the left-hand fit quality very much, and then you would have the increase kicking in at the ionization cavity.
I mean, if you look at this error bar, that, at the upper side of that takes you right to Jupiter, because Jupiter is 5.2 AU, give or take. So, anyway.
I can't compare on average, but whenever it encountered Jupiter, it was less than 5.
Okay. So moving on to the proton speed, we also looked at the radial component of it, and it really doesn't look very different, and Milan, you scooped me. We see a very clear increase, a very steady speed once you get past Venus, but before Venus you do see this clear indication of ongoing acceleration in the solar wind. Everything. Correct. So this is not just the baseline solar wind, this is everything. I mean, though you could say this is roughly the baseline here, that's 10%, the 10th percentile. You were looking at the 3rd, but close-ish. And, but yeah, so you are getting significant acceleration well outside the Alphane critical point. If we're looking at speed, we might as well also look at density. Like speed, we fit it with a singly broken power law. It has a pretty steep fall off, and I mean, this is a relatively weak break. And just as a consistency check, you can say, okay, we can look at the, how the density and the speed fall off, and if you add those exponents, those power law indices, both before and after their breaks, you get roughly -2, which you would expect density and the product of density and speed to fall off at about 1 over r squared. if you're assuming a conservation of particle flux density and have a radial steady state flow. So I'll mention, we also looked at plasma beta. Plasma beta, actually, we didn't need to put a break in part because there's just such a wide variation at any given distance. In fact, the variation at any given distance is far wider than the variation across 3 orders of magnitude in distance. And it's interesting to note that plasma beta really, for the vast majority of the heliosphere, is well within an order of magnitude of beta equals 1. You don't consistently see very high or very low beta anywhere in the heliosphere. Just to wrap things up, we are funded by a NASA grant to continue this work. One thing we want to do is increase our data. So, of course, some of the spacecraft are ongoing, generating new data. We also want to add in solar orbiter and look at some other parameters and add in some more sophisticated models. But one big thing that we want to do is to say, well, let's not look just at distance from the sun, but also heliographic latitude. The coverage isn't great there. We have this plot showing just the trajectories through this lambda R space. We'll be relying a lot on Ulysses data, but out in the outer heliosphere, it's actually not too terrible. We have some decent coverage out there from some of the spacecraft. So I'll leave up, in the interest of time, I'll leave up I'll just go through these quickly to say that we've produced these radial trends. We've submitted the paper to AppJ Supplements that'll have the data and the fits. If you're interested in an early release of them, please let me know. I'd be happy to share those data with you. In terms of the applications where I think they'll be most useful are first the planning of deep space missions. So you have an instrument that works at one distance from the sun. How do you redesign it to work at some other distance from the sun? And then also the validation of global simulations, because you would hope that if you have an ensemble average of these simulations, that you should be able to get similar radial trends to what we have here. So thank you so much.
Thank you. Any questions?
So in your radial trends, did you include all types of latitude into those fits?
Yeah, the only latitudinal cut that we made was, this is a good question. The only latitudinal cut we made was on the Ulysses data. We said after the Jupiter encounter, we removed it. We were a little concerned about the Voyager data because they do get pretty far out of the ecliptic plane. It was something we had our eye on, but when we looked at, I only included for the, I only have it here for the magnetic field, but we have in the paper this plot, the individual spacecraft unscaled data, and we didn't really notice any scatter between the spacecraft out there, which we took as an indication that it's close enough to being planar out there. We do have that, we are planning now on starting the joint R lambda study, which I think will resolve that issue. But in the interest of kind of getting this out, we said, well, all right, let's include it. But I agree that is a valid concern.
Any further question? Yes, I come.
Hi, this might be a stupid question, so I apologize in advance.
No.
When you showed the velocity plot, proton velocity, I was assuming that what was referred to in the baseline in Milan's talk would be the bottom of the bars.
Very roughly, yes.
But the bottom of the bars don't show the trend unless I'm looking at the wrong thing.
Well, I mean, he was looking, I mean, Milan, you were looking specifically at the 3rd percentile. And so the bottom of the bar is the 10th percentile, so that might be part of it.
Maybe the data set that you have for Parker Solar Probe, how many perihelion do you
I forget how many encounters it is. It's not the bleeding edge. It's a little out of date because it took a while for us to process the data, and we restricted ourselves to using the public data. And it's also lower cadence data. I only have the year, but we stopped at 2021. I think it was early 2021 at that. Yeah, it's predominantly slow wind. So, I don't know. You need to invite me to Moudon and we can talk over the data. I would love that. I've never actually been to France, but I digress.
So, I just wanted to ask, you're claiming that the magnetic field has a strength that looks like radial, up to about half an AU, right? The radial structure is supposed to be terminated in the Parker model is at 10 solar radii.
I mean, is that close to radial? I would say my expectation would be once we have more Parker Solar Probe data, especially data within the critical point, that this will be even steeper. I mean, I don't think that the doubly broken power law is a very physical...
But isn't this extending way too much, that 1.7? I mean, I would have expected to be already 1.
Yeah.
At around half an AU.
I don't know. We haven't tried fitting the Parker model yet. That's on my to-do list. I'm very interested to see how well it lines up and if there's any discrepancy or if there are any other models that we should be trying. I can only say that's what the data show.
Well, the average winding angle at 1 AU is something around
45? Yeah.
So that means you must have a mixture of the two scalings.
Oh, that's true. And it is a mixture. It's not, you know, one type of wind. There's quite a bit of spread.
Yeah, what you also probably need to take into account is that this total B is not just the Parker spiral, because it's B0 plus delta B, and the relative importance of delta B to B0 gets larger with distance. So, and crucially, they have a different scaling.
Yeah.
So this can keep the power law of B different from what would be the Parker spiral.
Yeah. And the 1 hour averaging helps a bit with that, but it's not going to get rid of everything by any stretch of the imagination.
There's still lots of fluctuations at 1 hour, right?
Yeah.
Okay, there are no other questions. So thanks, Bennett.
Thank you.
Thank you. Thank you. Now we move to the next talk. Given by Emanuele Cuesta about isotropization and evolution of energy-containing eddies in solar wind turbulence. So analysis from many spacecraft, no? Okay.
Okay. Hello? Is this on? Is this on? Yes. Okay. So yes, my name is Emanuele Cuesta. I am a fifth-year graduate student at the University of Delaware, and I am giving a talk on the isotropization and evolution of the energy-containing eddy size in the solar wind with, again, more radial trends. I do a mixture of Parker Solar Probe, Helios 1, ACE, Wind, and Voyager 1. So I'm going to first go into some background, some definitions, simple ones, and then some methodology, and then I'll go into the results of the alignment angles and the correlation lengths that I compute, and the ratios between those that are parallel versus perpendicular relative to the magnetic field, and then just a quick summary. So some background. So MHD fluids, they like to present some anisotropy related to the direction of the mean magnetic field. In this study, we particularly focus on gradient or correlation anisotropy, the outer scale, which has been found to be less than 1, this ratio, parallel to perpendicular, less than 1 in the inner heliosphere, closer to 1 AU is reversed. I'll show that more later in another slide. But this kind of anisotropy is very important in many different topics, including plasma dynamics, turbulence transport, and particle scattering. So here I have these plots from Matthaeus et al. In 1990, JGR, that look at the sort of Maltese cross plots of wave numbers, and the contours represent the energy. On the left, the energy squared, the magnetic energy squared, or energy. And so you see that there is a preferred direction that the energy is stored, which in this case is along wave vectors perpendicular to the magnetic field, because in the simulation there was a velocity share that had a imposed strong DC field in the x direction. And on the right, using ISEE data, they found that the separation, this is a 2D contour plot of the correlation function, and they show that there is an elongation along in the axis that is perpendicular to the magnetic field. And so there is definitely some connection when you try to find the contour plot of the magnetic energy for this situation, that there's a connection between whether the actual outer scale prefers to be longer in one direction versus the other, and the actual energy that's stored in the other component accordingly. And so this also was recently studied by Bendiopadhyay and McComas, where they looked at PSP encounters 1 through 5, I believe, and they focused on within the inner heliosphere less than 0.3 AU. And they generated a similar Maltese cross, where here this kind of shows that there is an elongation again in the perpendicular frame, and what this may mean is that the energy is greater in wave vectors parallel to the magnetic field. So this suggests that, again, energy is being injected along the magnetic field within 0.3 AU. And so what I do in this study is look at the correlation length, and what I do is that I use the Blackman-Tukey sort of correlation function, where if you look at the 1/E folding time, then you can convert to a spatial scale using Taylor's hypothesis, which is very more or less valid in the inner heliosphere, where it becomes slightly less, but more so at 1 AU and a little bit further on. And there's some other method that we also can use for computing this correlation function, which is via some log fitting to a function that is not normalized. But they're very similar when you use both methods. And so if we look at the alignment angle, so another big part of the study is to take into account the sampling direction of the spacecraft, which is taking measurements relative to the velocity, and the magnetic field may or may not be aligned with that flow. And so we want to look at the angle between the magnetic field and the velocity, which is particularly this function here, which is dependent on the arc cosine of the product here divided by their averages multiplied together. However, this is really important when using PSP data, because towards PSP perihelia, the spacecraft velocity tangential to the radial field is much stronger or greater, and although in some cases the spacecraft was found to be in near co-rotation with the sun during perihelia, it did have some effect in making the Taylor's hypothesis less valid. However, it was very important to use this definition here, because the flow velocity was not always being measured exactly radial. However, whenever you move further out, the velocity is becoming more and more dominantly radial. And so you can use some simplification to where you would only need the magnetic field time series to compute the sampling direction. And so this is the definition that I use for PSP. However, this is the definition that I use for ACE, Wind, and Voyager 1.
So you're saying this
Yeah.
solar wind is not radial? Is it verified at all scales, or it's only small scale and any fluctuations that give you non-radial components?
I believe that the components of the velocity vector, that the radial component is the dominant component, that is, at the heliocentric distances of 1 AU and greater.
Yes, but you say that they are, this non-radiality that you mentioned.
In the ecliptic plane for that ACE, Wind, and Voyager 1 measure, that is. Perhaps I'm not understanding the question.
So I just want to understand how physical is it, the non-radial solar wind. Is it just alternating fluctuations that are added on top of it?
of solar probes that goes really fast.
Oh, okay, it's solar probe results.
There's also very large non-radial fluctuations in the velocity near the switchbacks.
Yes, but this, exactly. But these are fluctuations. It's not like a mean direction. Fluctuation.
It's what?
Fluctuations, right?
Yes, but I believe these kinds of fluctuations could be found to be affecting this angle if I was to not consider the general V solar wind definition. If I just use this, I found that the function confuses sometimes those fluctuations as being anti-correlated, and then you take an average and it shows that it's parallel when in fact the whole interval is more perpendicular to the magnetic field. And then just whenever the angular bins that I use to separate out the perpendicular to the parallel correlation scales is kind of broad, and this is because you don't really see things that are too close down towards 0 degrees unless you're closer to PSP perihelia. But then conversely, you don't see things that are closer to 0 degrees further out using Voyager 1. And then that whole argument flips for perpendicular. You see more perpendicular intervals past 1 AU, but not so much in the inner heliosphere. That's why I'm using such broad bins. And so just to look at some sort of radial variation expectation, some fundamental scaling, I take into account these relations that are related to the turbulence speed, Z, and the correlation scale, L. And if you solve for these of the correlation scale L in terms of time, you get to the square root of T. And then again, motivation of Taylor's hypothesis, you want to convert it to a spatial scale, and you get square root of R. And that is independent of a sampling direction, which I have shown here on the right, where I both also do not separate out solar wind speed. This is just every single data point that I get. And as you can see, there is definitely some R to the 0.43 beyond 1 AU in the using Helios from 0.3 to 1 AU. It's a little bit sharper of a 0.62, greater than the square root of R. Other studies have actually seen in Voyager 1 that R is 2 to 0.44, so that's consistent. And then I also included just 3 6-hour intervals from PSP, the first 3 perihelia, and they showed that this is some sharp drop in these radial trends. And so this is another motivation for the project that I'm presenting today. And so this is just some data specifics. I could breeze past this, and if you have any questions, I'll come back to it. But I guess the general thing is that for all data sets, I'm using 1-day interval sizes, except for PSP. For any interval that's past 0.3 AU, I have it as 3 hours, and if it's within, then 1 hour, because I want to try and get as many perpendicular angular bins within 0.3 AU as possible, and there's not too many, even with 1 hour interval sizes. But then the correlation time within 0.3 AU is as low as 10 or 5 minutes. So the interval size of 1 hour is also pretty okay to use. All right, so here I have a radial variation of the alignment angles that I'm calling theta BV and theta BR. And as you can see, PSP is sampling generally parallel orientations within their perihelia here. This is within 0.2 AU. But as you move further out, this the average, an average of a vertical slice is increasing, and out towards 1 AU, it's so dark that I'm also including here ACE and wind, which is why there's so many, which is why it's black right there at about 50 to 60 degrees, and then Voyager 1 out, which shows it continually increasing towards 90 degrees. And if we look at the correlation scales, so here on the top panels, I have in blue the parallel scale, in red the perpendicular scale. As you can see, within 0.2 AU, there's barely any perpendicular intervals, but hopefully with future perihelia, there's, with future perihelia of PSP, we can keep on adding to this sample. To the sample size there. In the center, I have a brief little glimpse of ACE and wind vertical histograms here, darker showing the average and then decreasing, or the higher concentration that is. And then when it's fading away, it's becoming less and less number of intervals that are contained within that sort of slice across the x-axis, or y-axis that is. And then I have Voyager 1 out, and as you can see with Voyager 1, nearly every single interval that I have is perpendicular. However, one thing I wanted to note here is that the if you can kind of see, if you continue this trend here in the red down into the inner heliosphere versus the blue one is a little bit steeper, which means that it's increasing at a faster rate as you move outwards from the inner heliosphere. And here I have the fitted slope power laws too. So here for the general one, within 0.3 AU, it's increasing at nearly linear scaling. Then you have also a nearly linear scaling for the parallel, however, a much lower increase for the perpendicular scales. However, this changes then within 0.3 and 1 AU, where I then look at the power laws here, and they all seem to be pretty even. They're all increasing at nearly the same rate, separately and combined. And then beyond 1 AU, although we have barely any intervals for the parallel scale, this is increasing at 0.64, which is, again, even more than what we saw before from the general. The scaling here is a little different from what I showed before because we did use a change of interval size from the previous study. And then also here for the perpendicular, it's also much slower. And so if we just look at within 1 AU, the ratio between the parallel to perpendicular correlation scale, you'll see that from about 0.1, this point includes data from 0.1 up to about 0.3 or so, then increasing up to about 0.4, 0.45, that the scales are becoming more and more one-to-one ratio. And that kind of suggests that here in the beginning, there's more energy associated with wave vectors that are parallel to the magnetic field, and that energy is then being transported into different wave vectors away from the parallel magnetic field direction. So it's becoming more of a 2D-like composition to increasing towards more of an isotropic regime. However, there is a dip from 0.3 to 1 AU. Not sure what that is so far. Perhaps it's the encounter to, I believe, mercury that could be dropping it down, but there's also a lot of artifacts in the PSP, SPC data where I don't believe I have data quality factors applied on this study, and I should have. But this is something I found out after. And then right here at 1 AU, where here I also include ACE and wind, there is a dramatic increase to larger parallel correlation scales. And this is an interesting feature where we aren't quite sure whether this is going to continue to increase, stay the same, or decrease past towards isotropization due to a few factors, which I have here on my summary, and I think I'm past my time, so I will go ahead and leave it up.
We have time for questions.
Yeah, very interesting, thank you. The presence of -1 spectrum at large scales means that you have always the trend in the data. So autocorrelation function cannot be calculated in a unique way. It really depends on time interval you chose. The bigger time interval you take, the larger correlation lengths you get. So can you comment? I mean, this problem was addressed by Vamsi paper, Jagar-Lamoudi 2018. So can you comment on it? Have you tried to verify your results as a function of the choice of time intervals, how stable the results are?
I did compare the rough range of the, so I guess a couple of things. So there was here for PSP, I first used 6-hour interval sizes, and I noticed that and this is what this break is too. It's due to a change of interval size from 1 hour on the left to 3 hours on the right. However, and that's kind of why I also broke up my power scalings, because I didn't want to pollute the fit between those two ranges. Right. However, I did also look into 6 hours. Yes, the answer is yes. But it's the actual scale itself increases with interval size, but all of your intervals, all of your correlation scales across the entire radial distance, if you increase the interval size, will just, I believe, add a factor that will be multiplied against all of your other scales. Oh, and that's another thing. I was also right. Yeah. So it was kind of twofold.
The ratio of the parallel to the perpendicular. That was the whole point of the study.
Yeah.
If you don't have any perpendicular intervals, you can't do it. So you go to smaller intervals and accept a little bit of more error in it.
There are many caveats to the study that we needed to kind of consider. And solar wind speed is one of them. The actual number of samples that you get depending on your interval size is also a huge factor.
Emanuele, you're also forgetting your predecessor, Joshua Isaacs.
Yes, that as well.
The interval dependence of a lot of parameters on interval size, including correlation length in 2016, and he found that if you want to get a correlation scale that agrees with the two spacecraft correlation scale, which is the real one, then you should choose about 12 to 15 hours at 1 AU. So that's the baseline of what you should use. Yeah. You can't afford to do it for this study.
Right.
Okay.
Yeah. Hence the 3-hour interval size for PSP. Yeah, yeah. Well, yeah, with Voyager 1, right, I had none. Barely. Barely any parallel, right. Well, with ACE and wind, I was able to use 10 years of each of them to get some sort of sampling of both perpendicular and parallel, but I'd imagine it'd also be, because the average is roughly towards like 50 degrees, 55, if I didn't use all of their data, then I would also find very minimal amounts of intervals for parallel.
Okay.
Maybe it's also consistent with Weeks 2010 paper, who shows isotropy at breakpoint. Weeks 2010, he shows isotropy of K and K vectors at breakpoint. So it's you have this one, ratio is one, so it's isotropic, right?
Yeah, yeah.
Okay, I will say to let's discuss maybe later the coffee break. We are very in big delay. So Lorenzo? Oh. I don't know. Okay, thanks, Emanuele. Now, the next talk is given by Lorenzo Matteini.
Yeah, let's have a break. I'm saying
Okay.
everybody doesn't want to sit.
How many people want a coffee break? Stand. How many not?
Shall we have a coffee break now and maybe a shorter one, just half an hour, and then we have the... And then we have 3 talks instead of 2.
We- 20?
With sugar is better.
20 past 4?
4:30. Yeah.
4:30, okay.
But it's what I was proposing. So
I do want to hear
so I can be sure you will be waiting.
That's the whole point. I'm sleeping. Well, not really.
Okay, let me check if you have
Especially because you went the first slide is It's a little high for Olympic jumping. Oh, just kidding. Olympic jumping.
Yeah, this program is
Good job.
that he surprised you with
And then whether also actually go into the other resonance. Can resonate with it. It's really, I tried to, right? Because it was doing like the Taylor scale as well, right? So which we get.
The plot that I showed us is general correlation as well. That paper has.
Yeah, nice. But I think that there is a little difference in the strong underground or you're right. It's the same starting first. Yeah. But underground. You're working with me for like. But this is the thing, and I think yours is the experience, right? Maybe with these institutions. One of the arguments that don't really think about actual mechanisms. We decided to think about, this is an influence. But it's your first time. There is no such thing as Emily is here. There is no. Wow. She's gonna bring her tonight. There is something at the resonance of speed. There's a shape of distribution. You can create whatever. Told you, right? Let's do it. So maybe it's. Yeah. Oh yeah. So maybe it's better. You can do it tonight. No. Or maybe it's. I don't know. But is it? You're actually gonna do it.
So you can talk all.
Emily doesn't know.
That doesn't exist.
Well, if somehow you could arrange to do it when Colleen was present, I think she would, like as a witness or something. Do it when you want to do it.
I was going to
especially when you were
interested actually some wine castle.
With the proton and electron.
Sounds like a good plan.
When these two collaborators start to overlap.
During this weather, it's really okay, if we do it inside, then
and then there's the
you do it at a fancy restaurant, but maybe it might be fun to do it.
Well,
20
they have some
around. Cheer.
There are some interesting ideas.
I don't know, take pictures, it might be fun, think about it. So, but it's your show. It's your show. Did you show?
I was also thinking maybe social, but I don't know.
What's the social dinner?
Yeah, I don't know.
People are usually really drunk at that.
What are we doing? What are we doing at the social dinner?
Ben will appreciate it.
Oh,
Emily is here. He's going to ask her in Florence somewhere.
Haven't decided where.
Oh.
Well.
But I have it with me now, so she doesn't find it in the.
So, if you wanted to do it more privately, the bell tower has a tremendous view.
Walk up to the top of the Giotto Tower.
Yeah.
Or you could go to the Piazzale Lorenzo.
Yeah. But at least the bell tower, you have something on top, so you won't get.
But you'll also be out of breath from walking up the.
Oh yeah, that is the disadvantage. I remember doing it when I was in high school, and I was visiting Italy for the first time with my high school Latin club. And we got up, and then it's like, okay, we're at the top. And it's like, oh, this is just the first platform. There are 3 more to go. And it was June, so it was hot, late June. Yeah, that.
At least here.
There's also another. Well, there's other places like there's a really nice, expensive cafe called Vivoire on the Piazza della Signoria with the David there and the city hall, what's it called, Palazzo Vecchio, and the statues and everything around. You could have like a nice drink and sit there. Even in the rain, you could do it there.
What about the bridge just east of Ponte Vecchio? So that then you have the Ponte Vecchio in the background.
Yeah, but it's raining. I mean, that's the Santa Trinita. It's a beautiful bridge, but I mean, if it rains, and then you also can drop the ring in the river.
Yeah, there's
really
that.
Right.
But yeah, if you're both feeling like a hike, honestly, that would probably be. I like the bell tower idea, but yeah, you'll be out of breath.
Or, it's not my favorite restaurant by a long shot. It used to be on my list, and it's kind of not anymore because it's too expensive. But right near the Ponte Vecchio, there's a restaurant called Golden View, where you can get tables right on the river.
Oh, yeah.
It's a very elegant restaurant. It's suitably expensive. But and if you reserve there, you can get right on the river, looking right at the Ponte Vecchio. That's why.
In the museum in front of
And in-
Botticelli. Yeah, although there are always huge crowds there.
Yeah, that's another one. You could go to
Yeah.
the Uffizi and go in front of La Primavera.
Or no, the Palazzo Pitti, because it's less crowded there. I mean, in front of the Botticelli paintings, there's always huge.
Yeah,
tours.
it's like 1,000 Chinese
yeah.
there at all hours, right? And
So.
not Yanwen though.
So yeah. A
Okay.
very nice talk. I was going to say, we
that's-
should have a meeting that focuses just on this sort of radial trend stuff. And I was thinking we could call it Solar Radial. So rad.
So rad. That
Yeah,
sounds.
I like that.
Yeah. You guys are the So Rad Club.
Yeah.
You, along with Milan.
Yeah, Milan.
Maybe Milan will hire you for a poster. Anyway, you have, in this city, there are many good places to
Yeah,
to
they do
give
something.
the radio
Yeah.
answer. But the real on-off switch is outside or inside.
Right. Yeah.
Do we have an update on the weather for
It's supposed to rain
It's to
all
rain all
week.
week. Yeah.
Seriously.
Seriously. Yeah. All week. Yeah.
A little bit of a
And the
quieter.
sun peeks out Sunday morning when I fly out. Great.
Yeah.
Yeah, because I'm trying to decide whether to. Any word on Jefferson, whether he's going to make it?
I think he's not.
Okay, because I was trying to decide whether to play hooky tomorrow morning or Friday morning to go to Sesto.
What's in Sesto again, besides the university?
Istituto Toscana Polania, their outlet store.
Oh, yeah.
For this company, they make domestic linen, tablecloths, things like that, and I'm absolutely obsessed with them. They do beautiful stuff. I ordered from a retailer in Rome one of their tablecloths, and I love it. And my mom likes it. And I promised her I'd get her a runner. But they don't sell online except to retailers. Their only retail is this outlet in Sesto.
Wow.
Yeah.
Where are you guys staying?
We're staying not too far from the S&M Basilica.
Oh. So we get some coffee.
Santa Maria Novella.
Santa Maria Novella, okay. Okay. Yes.
So like from the restaurant, the pizzeria for tonight, 10-minute walk.
Yeah, yeah. Just cross the Ponte Vecchio and make immediate left and go 100 yards.
Where are you bringing them?
Huh?
Where are you bringing them?
Palazzo Tempi, pizzeria in Piazza Santa Maria Sopran. It's not fancy. Oh, it used to be a nightclub back in 2006, but it turned into a pizzeria. It's an interesting story. It was bought by or leased or whatever by an Italian family that used to run a pizzeria in the suburbs. And when they first started the place, like 2007 or 8, maybe 9, the organization approached them and said, you have a new restaurant, if you want customers, you give us like €1 for every customer we sell, we send you, or something like that, or €3 or something. And they said, it's fine. And for several years, they had no referrals from hotels. But the Italian people come into the city mostly on weekends when off season with their kids and stuff like that, discovered that there was a pizzeria directly across from the Uffizi with no tourists. And so the Italians started filling up this restaurant, and then it got high ratings. And it still doesn't have a lot of tourists, and it's really good. The pasta is excellent, and the pizza is good, and the house wine is good. If you won't spend the same money that you do in most of the restaurants around here. Yeah, it's a good place to. I mean, I called Maria up today, the wife, one of the owners, and I told her. No, I talked to Silvano, the husband, in Italian, and I told him that we had our Congress this week, and we had a lot of people who wanted to come get a with the pasta. So can he seat 22 people? I said,
That's big.
yeah.
You have so many.
Yeah, I said, maybe 24, maybe 20. He said, no problem.
proposal. Yeah,
You're probably going to see your parents or something.
Well, exactly. I'm leaving tomorrow.
Oh, you're leaving, okay.
And then, so yeah, so that's the last.
You're leaving before the social dinner?
Exactly.
Leaving before my talk? How can you? It's all right.
Maybe you can just bring it here. It's warmer here, yes. Ah, this is the new version of the program because I have an old version. Everything is mixed up. Okay.
So here it is, for example, an example of discontinuity. So this is the full field magnetic field during the interval of 200 seconds, and the black one is the magnitude of the magnetic field, yes. And you see a small jump of the magnetic field, yes. But at the same time you have a non-zero normal.
Did you rotate the reference frame?
Yeah. So this is the reference. This is the minimum variance reference frame. And yeah, the
Of
problem
this data or of this data?
of this data, and so B1 is the most variable, which is and B3 means the less variable direction of the magnetic
The blue
field.
one.
The blue one,
Yes.
yeah. But so usually, due to the divergence-free condition, the normal should be constant, and it is supposed that the third component is normal one. But in fact, there is because of some fluctuations that are not related to the current sheet, the minimum variance method it can mix the second or third component of the magnetic field. So, but even if
Yes, because it should be centered in this region, in principle. But
To do minimum variance, you
Yes.
say, Francesco, yes, not include all these things,
yes,
okay.
but I don't know
Yeah,
if it is
maybe.
enough to have
Yeah.
significant statistics if you choose it to short.
Yes, maybe change a little bit to
Yeah.
play with it. But this is the plasma here. What Sasha
yeah, but
checked is-
so this is magnetic field fluctuation normalized by the average by B0, and velocity normalized by alpha velocity, and the jump is like simultaneous in both variables, but the amplitude is not corresponding well. Although you can observe in other examples where the correlation is with this is not a current sheet, but
maybe we can stay with the same example and then go on.
It's very sharp, however.
Very sharp.
Yeah, it's
but
very sharp. Yeah.
what Sasha is doing also, maybe, can you that we see the whole picture? Yeah. So you see the total picture. Can we see the total? Yeah. So what he's looking at, you see, this is 0 time. It's the same time. And this lasts 0.1 second. This lasts 2 seconds, 200 seconds.
Okay.
And this is Russian dolls. Yes.
Yes.
And you see how polarization fluctuations change from scale to scale. But plasma, Sasha tried to interpret already the physics of this thing with the plasma. So this is the plasma parameters. So.
Yeah, so this is the raw data, and this is inertial range filtration. This is the ion scale filtration, and this is sub-ion scale filtration.
Denise showed presentation today about these scales. She just selected this. And Sasha looks through all scales at the same time.
Yeah.
And so using all this data, we cannot conclude what it is at this scale.
The plasma data is have enough resolution for MIGD, but not.
But here still you say
This is an
we have 1
enlargement
point.
of that?
That one.
No. This is an enlargement of that?
No, it's the same.
No, it's the same. You see
Just
the gray
this is a
line. This is
filtered.
filtering.
You take off you take off very large scales, and you keep only image the inertial range.
Yeah, this is the frequency filtering. I can show the windows that I use to
In
filter.
the spectrum.
Yeah, so the red one corresponds to the inertial range fluctuations. The green one is ion scales, and the blue region is
Sub-ion
scales. And we're trying to characterize the structures from.
So these are the largest scales?
Yeah,
the rose part without very, very large scales. You saw maybe it was this part, Sasha take it off.
Okay.
Yeah.
He just considered
Also this?
Yeah.
Yes, and also
so
this.
This is why you don't see anymore the
Small
jump.
scale. The jump.
Okay.
The jump, yes, we do not see the jump, but maybe it is a little bit on the right or on the left. The jump. Is it exact 0, this jump?
Here we don't see the jump because the width of the jump is around 1 second.
And this
and
is...
these fluctuations are much smaller. If we apply filtering on the scale which is smaller than the scale of the current sheet, then this current sheet is not
Yes. So what is the scale of this current sheet? It's not
about
this
the second. About the second.
about this.
Yeah.
So it should be few seconds.
Yeah, yeah. In
Let's say few
Yeah,
seconds.
few seconds, yeah.
And so these are plasma parameters, and you see density change a little bit. Velocity, there are 3 components, so there is a flow across the boundary. We do not see any like zero velocity
So
component.
in principle, is not a tangential.
It's not tangential.
Yes.
No. But the model of magnetic field is not constant on 2 sides. The black line is magnetic field, so it's not rotational either.
Yes, but it changes very, very little.
Yeah.
Yeah, okay.
So
20 nanotesla.
No, not 20, 10.
No, between 90
90
and 110.
Okay, well.
20, it's a lot. 20 for 100, it's a lot.
But here it seems to be much smaller, no?
Yes, it's the same, but it's between minus 100 plus 100, and this is between 90 and 110. It's a zoom in y-axis. Yeah. So yes, so for you it's more rotational discontinuity, even
Maybe, I don't know.
or not planar stuff, right? Or it is not planar.
Could not be planar.
Not perfectly planar.
Because the classical, let's say, the classification
Yes.
is for planar structures.
Yes. So yeah, or maybe there are some upstream, downstream phenomenon that makes it not constant parameters on both sides, and then it's But okay, anyway, it looks like more planar than what Sasha has later. Look, this is like not so planar then.
Yes.
Yeah. And this, so this can be rotational, right, Sasha? This was your interpretation?
Yeah, so we see an arc which is a signature of
stay this way,
but at the same time you have this decrease of the model of magnetic field like a tangential
Yeah, but on the
discontinuity.
scale much larger, because the scale of the current sheet is like
it is this one you say.
this one, yeah, and the scale of the magnetic depression is much larger. So in the area of magnetic field depression, you see a thin current sheet.
Magnetic field depression, yes. But
So
this polarization
this-
comes
yeah, I
from
mean-
depression, no? Or it comes from current sheet? This arc
This arc, it comes from the green component that
within the current sheet.
within the current sheet, which
Okay.
goes up because it tries to compensate locally.
Okay.
So that
Okay, so it can be rotational discontinuity, this thing.
yeah, I think this is more rotational discontinuity.
Yeah, the first one may be tangential. No, because we have a flow across the boundary. But yeah, the mixture. Yeah, it's complicated. And these are temperatures: proton temperature, electron temperature.
And temperature changes from the 2 sides.
What you see, I mean,
Here, yeah, the proton temperature changes.
a little bit. Yeah.
Yeah. A little bit, just right on the
scale.
on the right, a bit on the right, from the center where the discontinuity is, because my method was centered on the smaller scale
Bill
structure.
Matthaeus will tell you that you have a heating here within the structure. But okay, the chicken and egg problem is not clear. What is first? What is next?
So this is USB-C?
Do you have any interpretation of this thing?
I don't know.
And
Probably
what
there's some mixed feature.
Yeah.
I suppose, yes.
I don't know if one could figure out this kind of thing.
For that one, I need a dongle.
For instance, imagery that one can perturb, for instance, a classical planar solution and see what changes.
What changes? Yeah. If there are theoretical walks like this, we need to look for somebody did this job. Yes.
They made this way, but
Shock structures have been studied a lot from this point of view. These ripples on the shore, but for tangential rotations continue, I don't know. Maybe for magnetopoles, people studied this surface weight as well. Do you know the names? Kellinger was stability, yes.
So we really
I raise my fist in it. And as a figure. Lots of cables.
You will need
Okay, are we ready? No? Yes? Okay, yes. Now we have Lorenzo Matteini, who will talk about modeling ion beams in the expanding solar wind, instabilities and heating. So, please.
So I think everybody owes me a coffee break, right? And right. So yeah. Okay. No, thanks. And I'll try to be on time. This year at this meeting, yeah. So over the last few years, I've focused on maybe larger scale. Now I'm going back to solar wind kinetics. Is that okay? Solar wind kinetics, in particular ion kinetics, which is actually the origin for me because it's what I did in my master thesis, laurea thesis in this place. So, and because of that, and because yesterday we had a beautiful day remembering Professor Claudio Chiuderi, who was the head of the group here, I also wanted to share some memories quickly. I'm taking this from the presentation, and because somehow my career is also related, as many others, to him. And in fact, despite I did my thesis, my laureate thesis, with Simone, with an important contribution from Petra as well. Simone was so young at the time that he could not be the relatore, the only one, so we needed a co-supervisor, and so Claudio did it. And by the way, the picture is a bit strange, but it's the only one that I had taken by myself, so I wanted to. And so he didn't really, so he was, okay, not really supervising, but I remember that when I had to prepare like the introduction for the thesis, which is the most important thing. So I gave him a draft, and he came back and said, "Okay, we need to talk." And so I remember me, him, and Simone. We sat in his office, and very kindly he was there. We described the work, and he started drafting the introduction himself. And I was very glad that I could still find the notes from almost 20 years ago, yes, but handwritten by Claudio, yes. And then, of course, he was the lecturer of the plasma astrophysics course. He was told yesterday already by many that it was probably the best undergraduate course we had, and it was the same for me, of course. I really liked it, and I'm very glad that a big part of that course is now in his book, which is not only in Italian but also in English, so it can be used. And I will actually use it at Imperial College this year. And finally, also he gave me the good advice for my Erasmus, because when I decided to go on Erasmus to France, in Paris, he then told me to go and talk to Simone Marcovelli, to get a link to the group there and to organize my project, Erasmus project there. This is how I started working in space physics, and this is when I met Milan, Olga, and okay, so I have just a couple of, couple of memories related to Cudery about my stay in Paris, because when I arrived there, I was sharing an office with a more senior academic, and who was there only in the morning, and I was an Erasmus student, so I was not there in the morning very early, and so for a bit we didn't meet. And after one day we finally met, so I said, oh, I'm Trius, I come from Florence, and then I tried, oh, maybe you know Professor Cudery, and he said, oh, Claudio, and in fact he was a good friend of Claudio, Andrea Mangione, and when I was there, Andrea had another Italian PhD student who was there, and so I met, and he was a young PhD student, and he said he was coming from a plasma group in Italy. I never heard of it before, Cosenza. It was okay, and he said, and then he said, okay, so working with Andrea, and said, oh, Cudery, oh, I got a lecture from him in the summer school somewhere. It was very, very nice. And you know what? Actually, the head of our group in Cosenza, Pierluigi Veltri, was the first, actually we discovered yesterday, maybe second, student of Cudery, at least. And so, okay, so I was happy because I was seeing how this nice legacy, and we heard yesterday how much exchanges between Florence, Paris, and Cosenza have been important. Many people in this room, I guess, have traveled between these. And so actually the last time I saw him was at this conference last year, and this picture has been shown many times yesterday, but not yet today, so I'm showing it. And it was taken during this workshop last year, and I think, okay, many in this room are there, right? Okay, I just wanted to... Yeah, and Olga took the picture. Yeah, I should credit Olga. Yeah, and since I think there are many people from Cosenza, you're maybe interested in knowing who was the PhD student in Cosenza 20 years ago, and it was, yeah. I don't know who is the other one, but yeah. Okay. I think, oh, maybe it's Olga. Yeah, actually, to be honest, I think it's a selfie before smartphones, but yeah. Oh no, come on.
Time is running, come on guys.
Well, I can send him the... I have, if you want, I have worse pictures than these for Franco, but anyway. I know he's very important now in the university, right? So maybe I can blackmail him. And anyway, yeah, okay, so back to the science. Yeah, so the topic is about ion kinetics, and particularly related to the motivation is, we know that in the corona, from spectroscopy, we know that ions are preferentially heated with heavier ions which are heated more than protons and electrons, and these conditions is then confirmed when we measure them in situ. Now we have Parker Solar Probe measurements here in between, so we can bridge this gap. And of course, we would like to know what is the cause of this heating in the corona. We don't know yet. But also, what we see in situ is that if we follow the temperature profile of, for example, the protons, even past 1 AU, it falls off less rapidly than adiabatic, meaning that some form of heating is there all the time. And of course, it's an open question whether the heating, which is responsible for the non-adiabatic profile, the non-adiabatic expansion of the solar wind, is the same of the one we observe in the corona. Because if it was, we could then link one to the other and use signatures. But if we want to explore signatures, we have to deal to the fact that actually these signatures of heating, all the non-thermal properties that we have in distribution functions, they actually change during expansion, just because the plasma is non-collisional and expansion is then changing the shape of distribution functions. But also the plasma can interact with turbulence, which can introduce additional deviations from equilibrium. But on top of that, the fact that distribution functions, as we have seen already today, are not Maxwellian, can be the source of instabilities, and in general, wave-particle interactions can play a role in all this. And so we need to understand and constrain these wave-particle interactions if we want to know if we want to assess how much heating is, for example, coming from the corona or coming from other sources, okay? So this is what we are trying to do, I'm trying to do in this presentation. When we use PSP, Parquet Solar Probe, now we can go close to the sun. This is what we see. We see that ion distributions are very not Maxwellian, very not at equilibrium. In particular, different ions, ion species, but even within one species, the protons, there are multiple beams. So there are different populations of ions which leave the sun with different speeds. So this speed difference, this relative drift, is actually a source of free energy in the plasma, because if you could reduce it, if there is some then deceleration, this is kinetic energy that you can make available for example, thermal energy, so plasma heating. And in fact, there are instabilities related to this state, because as you know, a plasma cannot support a too big drift between species before getting unstable. So typically, the Alfvén speed is the natural boundary for how big this drift can be. On the other hand, if we look in detail at this distribution, not along the magnetic field where we see the drift, but also taking into account the direction across the magnetic field, we see that there are signatures of scattering, actually, and this was what Trevor was discussing, and I think this is there is indication that wave-particle interaction possibly arising from instabilities are at work in shaping this distribution. So how do we describe this? Then to do that, I'm going to show you results from kinetic simulations so that these simulations can self-consistently describe the evolution of the distribution functions and the interaction with electromagnetic fields in the box. But at the same time, the box is coupled to, well, evolves in time in a way that it mimics the expansion of a parcel of plasma as it goes away from the solar wind. This is the expanding box model, which is another product of this Florence-Paris collaboration back in time, and which was implemented in this code by Petr. And so I'm going to show you then results of these wave-particle interaction and instabilities of the ions, but not just in a local framework, but in an expanding one, so that, because what I want to show you mostly is not the detail on how this interaction works, but how this changes with distance from the sun, and so what are the average properties that we get during expansion. To do that, I initialize a plasma which is made up of 4 populations, because this is what we see in the solar wind. We have a proton core, a beam, and then alpha particle, which also have a core and a beam. So if we start and we consider just the drift between the proton core and its beam, we see that after some distance, this starts to decrease. To understand better this, it's better to normalize this to the local Alfvén speed. And what happens is that even if I start with a drift which is initially stable with respect to plasma theory, because the local Alfvén speed during expansion decreases, just because of how the Alfvén speed scale with B and N, the beam will become super Alfvénic and then unstable. And at that point, it starts to be reduced because waves are produced, they scatter the particle, and associated to this beam deceleration, there is some anisotropic heating or preferential heating for the different populations in the plasma. This is exactly what I mentioned before. We have some kinetic energy in the form of drift, some free energy in the form of kinetic energy of the drift, which is redistributed towards into thermal energy, so increasing the temperature of the plasma, and in particular in the perpendicular direction. So we get anisotropic heating of the protons, in this case, because the protons are the species which is most unstable here. So this means, if we look at distributions, that we started with protons and alphas made up of two populations drifting with respect to each other, and we end up with things which are more elongated in perp, with contours which are indeed the scattering contour expected, more or less those expected from quasi-linear theory and consistent with what Trevor was saying. I think we can add something else here, because here, so this is what you would typically observe when you have an instability, but here the source is not from the source of the energy for growing the waves responsible for this scattering. It's not the thermal energy of the plasma. It's the relative kinetic energy of the population. So in terms of the waves which are produced at expenses of this drift, the scattering that you obtain is actually a scattering which goes in the direction of heating the plasma. So it goes in the direction of what Trevor was saying. We would expect, I expect that if you do your analysis to this distribution, you will see that these are consistent with plasma heating and not cooling in terms of scattering. But
what's the difference between the top row and the bottom?
this is at the beginning, this is after some time. Oh yeah, I should run. Yeah, okay, yeah. Yeah. R0 is whatever you want, in the sense it's the initial R0, and this tells you how many times in terms of the characteristic time of expansion you have, well, how far you have gone in terms of your initial distance from the sun. So if you place it at like 0.1 AU to mimic what we observe in Parker Solar Probe, this can be up to 0.3 AU. And yeah, but it's a relevant question, because the point here, if you want to compare with observations, we need to address this normalization. So it's better to do that in a parameter space. And sorry, and this is I would argue that these are similar to what we see in situ.
How can we tell from this plot which parts of the evolution are due to expansion?
I'm coming to that. Yeah, and to do that, we're gonna look at some parameter space. So now there are two main parameter space which are used in the community, and they are quite consolidated thanks to the Helios observations and by Martian too. One is in the anisotropy as a function of the beta, and I'll show you a better part. Well, we have a well-defined correlation or anti-correlation of the anisotropy with the beta, and one is the drift speed we normalize to the alpha speed as a function of the beta again, in which case the correlation goes up. So these are not only valid for where if we collect in this parameter space the evolution of the protons, and the different colors are distance, and alphas, we see that while the protons follow this Martian 2 anti-correlation, which is well recovered in the simulation, the alphas, they ramp up along this marginal stability path of the alpha instability, which is what we have in the simulation. So the main points for this part, which is the only part, are that ion instabilities are triggered during expansion, and as I said, consistent. The results are very consistent with data both for the beam and the associated evolution of the anisotropy. And alphas are rather unstable to the Freilos instability. Just to show Bill, if you actually, one can look at many other things, like for example, what are the fluctuations you can you obtain, and for example, the spectra. And this is just to show that when you do 3D simulations, which are not those, you recover turbulent spectra, mostly like those that you observe in solar wind. You can explore if you want. And just the last note that you can also use this type of simulation to study, instead of kinetic physics, small scale you can use to investigate large scale. And for example, the evolution with distance of large amplitude alpha waves, and recover what we call the spherical polarization as the plasma expands, basically as we observed in solar wind, that the magnetic field fluctuates on a sphere of constant radius. Constant magnetic field is what we observe in the simulation as well, and because of that, then we have the appearance of magnetic field switchback when fluctuations delta V over T becomes of order 1. But this is just a side note that to advertise another paper. But reading the conclusion.
I'd like to make a comment.
You can ask two questions then. No,
Maybe even, who knows, maybe three. But if you're calling it a large amplitude Alfvén wave, and if it's in the MHD regime, then it follows logically that it's, quote, spherically polarized. There's no ambiguity there, right? I mean, MHD Alfvén waves, compressible MHD, are spherically polarized.
Okay, I think...
Read Barnes, 1979.
I did.
I mean, so it's not a, there's no logical jump there. It's a tautology.
I don't think that's so easy, but that you can get spherical polarization. And for me, it's the first time that I see anyone saying they see spherical polarization in any MHD, like incoherent, this type of simulation where you don't start it. I know, of course, the baskets and Olbeck.
Olbeck, 1974.
Yeah, all this work. Yeah, but it's not. But that's different. Well, this follows from that.
Alfvén waves are spherically polarized.
Well, I agree they are, but no one knows why. Right?
Read Barnes.
No, one is just saying that. Well, one thing is to say that a spherical polarized wave with constant V is a solution of MHD, and I think everybody agrees on that. One thing is to say how do we reach this state and show that this happens in a simulation.
When you use the word Alfvén wave, if it's a wave, then they're not interacting with
Sorry,
each
these
other.
are not waves. This is okay. Okay.
Oh, okay. I'm sorry.
Yeah. No. Okay. This is not a wave. Sorry. That's
Okay.
why I'm sorry.
We are out of time. Oh, you like to conclude? Conclusion, okay. Okay, let's thank the speaker. Okay, there are two questions. In the meantime, I ask the next speaker to get ready.
Lorenzo, do you think... Sorry. Excuse me. Please conclude. Do you think that for the last issue, the expansion is crucial or not?
No, because we do see that it starts forming some
For the question? Yes. Okay.
expansion is not important. So in this experiment, expansion is important because it grows delta V over B, so it makes you go towards the sphere. But no, it's not. The answer to expansion itself is not.
So if you do the same simulation without expansion, you expect to find the same.
Well, it depends on the amplitude. Yes, but yes.
The answer is yes.
Yeah, the answer is yes.
Yeah. Wait, Lorenzo. So can you go back to your plot with the heating? So can your model actually resolve the presence of waves? I think go back to more slides. Yeah, these guys. Right. So to make these hammerhead distributions, what you really need are fast magnetosonic waves, and I think you can't actually heat those with ion cyclotron waves unless you have. Or basically, you have to have inward going population of waves at a very high wave number to do it. So can you actually go into your model and look at the wave populations and figure out if those are there to actually cause this? Sure.
So they are more than ion cyclone, they
Right. Yeah, basically, I think, as I'm saying, if you really wanted to compare this to the observations, I think you'd have to go and look at the wave populations. Pretty much, yeah. The electric field helps a lot, so sometimes. Yeah, cool. Thank you.
He will talk about on the role of solar wind expansion as a source of Whistler waves.
So, hello everyone. I'm going to show you some results of a fully kinetic particle in a cell simulation to study the role of solar wind expansion as a source of Whistler waves. And we investigate how these Whistler waves can scatter the suprathermal electrons and then regulate the heat flux in solar wind. I will just give you a very brief introduction about how electrons look like in solar wind. They are often consisted by a thermal, almost isotropic core, while at higher energy one can see a suprathermal halo population distributed at all pitch angles, and then aligned to the magnetic field a suprathermal strand. Recent observation by Parker Solar Probe has shown that in the vicinity of the Sun, while the halo fractional density represents only a small percentage of the total electron density, the strahl is more pronounced. On top of this, we know from observation that while the halo fractional density increases with the heliocentric distance, the strahl fractional density decreases. So both the halo and the strahl carries most part of the heat flux in solar wind. So it's clear how these densities change between suprathermal electrons, between halo and strahl population, and how the heat flux is reduced in the heat flux should be two related mechanisms. And we also know by PSP observation, but also at 1 astronomic unit, that the heat flux carried by the solar wind is suppressed below the values provided by collisional models. So wave-particle interaction can play a fundamental role in regulating the heat flux in the solar wind. And one of the most invoked processes to explain the non-collisional regulation of the heat flux in the solar wind invokes Whistler heat flux instability. And Whistler heat flux instability that produce Whistler waves in the solar wind. Whistler waves that have been observed also recently by PSP with propagation angles
going from quasi-parallel to high oblique. So what we want to do is to study the solar wind expansion and look at the kinetic electron scale to see how is the interplay between solar wind expansion and kinetic instability. To do so, we employ the expanding box IPIC 3D, which couples an expanding box model with a fully kinetic particle in a cell approach, which gives us the possibility to look at the electron scales and to employ realistic parameters, realistic mass ratio, realistic characteristic frequency ratios. So what we do is we perform a two-dimensional expanding peak simulation, and we model an electron velocity distribution function whose parameters are in line with those observed by PSP during its first perihelion. We modeled an electron velocity distribution function basically made by a core and the strahl electron. The strahl is modeled as a drifting B-Maxwellian distribution with a certain anisotropy. And we observed that with this distribution, the electron velocity distribution is completely stable to microinstabilities. What we want to see if it naturally evolves toward a stable condition thanks to the solar wind expansion. And why we do so? Because we know that the growth rate of the Whistler heat flux instability strongly depends on the ratio between the strahl drift speed over the Alphen speed. Here in these first three panels that you see on your left, moving from left to right, the strahl drift speed over the Alphen speed increases, and together the growth rate of the instability increase, and the threshold of the instability becomes lower. So we know that if we consider a magnetic field which is predominantly radial, the Alphen speed decreases 1 over r. So the question is how the strahl drift speed decreases with the heliocentric distance. It is slower than the Alphen velocity or not. And what we observe here, you see on the first panel on the left, the ratio between the strahl drift speed over the Alphen speed. And because of the adiabatic expansion, the decrease of the strahl drift speed is less steep than that of the Alphen velocity. And you see an increase of this value until these yellow points. This yellow point coincides to the heliocentric distance, to the time of our simulation when our plasma crossed the threshold of the Whistler heat flux instability. And then the plasma is bounced back to a stable region. And it undergoes to these cycles of destabilization and relaxation of the instability. You see that it crosses the threshold of instability, then it's bounced back to stable region, and then because of the expansion, the ratio increases again and then decreases. So we have two concurrent mechanisms. On one side, the expansion and then the excitation of Whistler heat flux instability. When the stability is triggered, there is the generation of Whistler waves that regulate the strahl drift velocity, and then the plasma is bounced back to stable condition. And you see the same behavior when we look at the evolution of the magnetic energy fluctuation. You see an exponential growth when the plasma crosses the threshold of oblique Whistler heat flux instability and relaxation and secondary instability at later time or higher heliocentric distances. When we look at the traces of suprathermal electrons and core in the anisotropy versus beta diagrams, so the Brazil plots, we see a redistribution of kinetic energy from parallel to perpendicular that's limit the development of the temperature anisotropy produced by the expansion. And you see that the suprathermal electrons, they never approach the threshold of phi rho instability, meaning that the
About the thermal evolution of the anisotropy of the electrons, are you imagining that the electrons are following the CGL expansion?
Exactly. So there is no. It's just an adiabatic expansion, so there is no... Exactly, yeah.
I guess it didn't work. Shouldn't work.
So
the fact that you have a double expansion adiabatic is given by the fact that the ions are super strong. Otherwise, the behavior of the distribution function is completely different. Is not conserving the shape. When you have the CGL expansion for the ions behave, they move the shape becoming a cigar-like, but the symmetry is preserved. When you take the electrons, if you make the same analysis, you see that the shape is like is moving, is accelerating. You can check in one of my data, but I have not in mind that I realized this is a work on the 7. So the GGL expansion doesn't work by definition for subsonic particles. So I don't see why you should have the CGL prediction for the electron.
It works in the expanding box.
Yes, basically you are forcing the system to behave in a way that is not the way it should be.
It's something a little bit analogy to what you expect.
No, because you should have some kind which is like a fish-like shape.
But you have collisions.
Okay, so you say, if you take the collision, you have an isotrophic correlate that is in account.
You might have collisions for the code.
yeah, that's like the model is to see how the, like, if we consider a radial magnetic field and alpha velocity goes down as 1 over r. So at the focus of the strand, basically, what happens when the strand focuses because of the expansion, if it's approach a threshold of some instabilities or not, so it goes away from this.
Okay, no, this is just about the CGL prediction that you're forced to follow.
Exactly, the idea is to force it to...
In the real solar wind, you are not forced to follow that prediction.
Right, that's
even if there are no collisions.
Yeah, I completely understand what you say. So the idea is to, exactly, to see, well, here the strand electrons are focusing, so we want to see with the heliocentric distance what is the reaction of the electron, because it's something that is observed that when we move away from the sun, there is first focusing, and then there is, when wave-particle interaction gets in, you have the strand distribution that broadens. And then basically you want to simulate this. So to go back to this plot, we see that they lay all at the center of this diagram, meaning that they never approach really the threshold of Pyro's instability. While for the core electron, we have a deviation to the double adiabatic expansion when the Whistler waves are triggered in the system, meaning that these Whistler waves are also interacting with the core electrons. And then because of the expansion, they cross the threshold of the oblique Pyro's instability, and they contribute to this second bump in the second growth in the magnetic energy. So here I will show you a couple of slides where you will have on your left some quantity, in this case the velocity distribution function as function of v perp and v parallel, and on the right you have the magnetic energy fluctuation, and then a blue line crossing it to see at which time of the simulation we are. And you see that there is a significant scattering of the electron velocity distribution function when Whistler waves are generated, and then there is the generation of a horn like in the distribution and a Maxwellian population that is generated from the scattering of the star with Whistler waves. Again, I will show you the focusing of the strand, then there is the generation of wave, first the adiabatic focusing, and then the resonance between electron and Whistler waves. You can see it also from the 1D cuts, so the orange line represents the cuts along the parallel direction, while the purple one along the perpendicular one. And again, you see a significant transfer of momentum from parallel to perpendicular direction and the reduction of the strahl drift's velocity. And then there is the generation of this halo-like population distributed at all pitch angle, which deviate from the Maxwellian distribution. We also went to analyze the resonance condition, in particular in this diagram moving left to right and top to bottom, the time increased, the allocentric distance increased, and with vertical line, the vertical line coincides with velocity at which the resonant condition with cyclotron resonance interaction with Whisper waves are respected, while the circles represent the diffusion path of the electron that undergoes to cyclotron resonance interaction. And then you see that the horns fit rather well with these circles, meaning that particles which velocity fulfills the cyclotron resonance condition are scattered toward higher value of perpendicular velocity. It's also interesting to see that these lines approach as the plasma move away from the sun, meaning that as the solar wind propagates away from the sun, it encounters conditions for scattering processes to occur. Here just you will see the generation of waves, secondary stability, and how these waves shift towards lower angles of propagation. Actually, you can see it better from the K parallel plot here. You see the generation of high oblique modes, then they shift toward lower angle of propagation, and again seconds mode when the core cross the Firol's instability threshold, and the strahl keep doing this process of focusing and scattering. Here you have the different snapshot. As I was mentioning, at certain point the parallel contribution becomes compatible with the wave along the oblique angle of propagation, and then secondary stability start triggered. We went to look at the omega k spectrum for the times when waves are mostly parallel to the magnetic field to understand in which direction they are propagating. And we observed that from the relaxation of oblique Whisper heat flux instability, there is a generation of quasi-parallel Whisper waves that are propagating sunward, and then anti-parallel to the heat flux, meaning that these waves can contribute to the heat flux regulation. And this is this was a quite apparent controversy, because it's well known that the strahl can produce only waves propagating the Whisper heat flux, parallel Whisper heat flux instability can generate only waves propagating in the anti-sunward direction. That's not able to reduce the heat flux, as well as the Whisper temperature anisotropy instability, which produce waves in both directions. We see that there is a consistent amount of waves propagating parallel and sunward. And finally, just to show you the effect of this wave on the heat flux carried by the electron, you see a significant decrease of the heat flux when waves are triggered in, and the heat flux is mostly carried by the enthalpy of the strahl, and but its bulk component, so the reduction of the strahl drift speed, is the most significant component for the total heat flux regulation, and also the heat flux exhibit these multi-slope behaviors in other bulk parameters. And yeah, I will stop here because
any question? Yes, Milan.
So I guess your simulations are kind of uniform. You have Whistler waves everywhere in the box, and what we observe is our patchy localization of Langmuir waves. We obviously, sorry, Whistler waves. We obviously do not observe them all the time. They are very patchy, and a small fraction of the time they are present there. So can you comment on this?
Plasma is back to a stable region, and then again. So my picture is that mostly parallel waves during the evolution of the system, but they are still happening on very short scale because the plasma is bouncing back and in the stable region. So it's.
But you cannot say anything with the simulations about the fact that there is a kind of feeding factor, and the Whistler waves in the solar wind they are not uniformly distributed.
Okay, look, I guess. So actually, there are oblique Whistler waves that have been observed. Close to borders, close to shocks, but not right. And also you see in this kind of picture that oblique waves, they are just like a temporary stages of this wave. Like they disappear and and there is a long part of the simulation which is dominated by parallel propagating these waves.
I have just a question. You see an acceleration of the strahl component with respect to the core component in the simulation before the instability start?
So they are counter steaming to maintain the zero current condition during the simulation, and what we see that there is an inverse behavior between the core and strahl different velocity. So the core velocity goes up while the strahl velocity goes down.
During the instability?
No, during the expansion.
During the expansion, the strahl is decreasing velocity.
Exactly, but slower than the Alpen speed.
Yes, slower than the Alpen speed, but decreasing the velocity.
This is normalized to the speed of light. So that's the real behavior of the straddling speed. So it goes down, you see until the yellow point, it goes down slower than what happens when the instability is different.
Okay, another question? Yes. Thanks, Alfredo. And now we move to the next talk and the last one for this day. We have Noor Rawafi, who will talk about magnetic field reconnection as the driver of the solar wind. Yeah, should work. Yes. No, not yet. No, it appears. Please go. Thanks.
Okay, good afternoon, everybody. I'm from the Astrophysics lab. I want to recognize the team here. Yeah, it's proportional to density. Yeah. not yet for connection with apps. Let me correct that. Yeah, this is more than double what we need. But that's not necessarily bad. It's a good thing. And the reason is also well, it's simple. Before you have the connection with open field lines to introduce the jet, you need to keep your plasma in the loops very hot. And the excess of connection that probably we are measuring is closed connection. And that closed connection is keeping the loops hot for the temperature, or at least close to the temperature. That when you have the jet lags, it's already a problem temperature. It's already this is the paper by Nice Farget and Stuart Bain, where they were basically saying, yeah, the scale size of the switchback patches fits pretty well with the scale size of the supergranules. What we are observing now is basically supports this quite well. Now, this is a good point. When you look at what it did 2021 or 2020, there were 5 papers, basically 5 models for switchbacks in one paper. And you can classify them whether they're foreign origin or principal origin. For the observation that they presented here, it doesn't really matter. Basically, whatever model you are considering, these events we are showing will produce ingredients for it. If we take, which one? This one, it's obvious. We have the connection there, so it's obvious. But this is where they are basically considering stiffening of upper waves. Yeah, the connection will produce upper wave or down, and they will propagate outward and potentially they will stiffen as well. This one as well, that's your model. We talked about it I believe yesterday. Same thing. The jets will naturally produce shear because you will have differential speed.
The thing that I don't get, Nor, is the connection between the presence of the jets and interpreting it as this kind of interchange reconnection.
Yes.
I don't get that. Did you show anything making that connection? I mean,
You're looking at the literature. When I introduced earlier the big X-ray jets, there are different models of connections where basically they are based on the interchange of connection between open and closed.
between open and closed.
Between open and closed, yes.
Are you pretty sure that you have enough regions of open and closed field lines coming together above the transition region to do that?
That's what we see. In the coral holes, it's very obvious.
What's that?
In the coral holes, it's obvious. But in the network elements, yes, in the network, you don't need all the network field in the white sand to be open to the corona. You don't need that. You need just a fraction of it. And when you look at spectroscopy, that's what we see. We see a subset of the network of up close above a certain network limits. Not so it's kind of. I think this is my last slide.
Okay, so thank you very much for your interesting talk. Any question? Yes, I come. And then I have also one. But
Thank you, Noah. May I just add something that the element abundances seen in active regions, like the FIP effect, does not match that seen in the solar wind. But the element abundances seen in an open field or something without a resonance do match the solar wind. And I'll talk more about this on Thursday afternoon. But I think the element abundance are arguments to support everything you're saying.
okay.
Very similar to the papers that you may know on the, I guess, and big topics that you discussed, that the papers by Wu and Shadiabal, where you have open magnetic fields which come from everywhere, not only from the poles, but from everywhere in the quiet solar.
Well, it's selected. For the coral holes, it's obvious. I mean, most of the fields are open.
Yeah, but also their claim is that also you have these open lines on which you have probably
I would say instead of everywhere, when you go to the point sun, you have a selection. Certain network fields are open to the solar wind, some of them are not. So it's, in a way, yes, but not as everywhere.
Okay, maybe in the meantime, I have a question also. Can be this jetlet, I mean, can be low magnetoacoustic waves?
But there is an issue there. This is actually a big problem that, I think we have lots of more observations and so on. You would have waves, yes, and you have to disconnect the sterling with these flows of waves. For the pulsing events, we are pretty confident these are flows. But you would have waves as well there, so you have to find a way out.
I just have a question, just a provocation of some sort, since these are so fashion argument. Is this jetlet or jetlet scenario or supergranular activity that you're mentioning somewhat related to the so famous campfires that are seen by solar orbiter?
That's really excellent question. And it's all connection.
Oh yeah, that's true.
The fundamental process of connection, whether it is closed field region or open field, it doesn't really matter.
Yeah.
What I believe that the campfires are some sort of jetting as well.
Yeah.
But it's just accepting closed field region. That's what it is.
But is the topology is different for the campfires from this jetlet?
Because the field is closed.
Okay.
The campfires are low lying. They are very, very low.
Okay.
Yeah, these are probably high lying.
Yeah, but people like not to go.
No, that's the speed of the plasma projection. For the alpha speed, we don't know.
But isn't the ejection speed from convection if the connection is the X point is in a plane, including the radio?
La velocità di alfa, no, anche di più, è maggiore. Perché no, è molto più vicino alla velocità del suono, 150.
Sì, ma poi non è che
Hai comunicazioni da fare?
Okay.
I think we can discuss at dinner. Thank you very much for a very interesting. So the session has ended, so we will continue tomorrow at 9 a.m. It's true? Okay. Other communications? No. Okay. Have a nice evening.